Yes, alles gut.
Let me try to gather you here.
Good morning, everyone. Welcome to Sofia. So, if nothing else, we have at least a good weather for you today. A lot of sun, a little bit of cold. So, this is conference dedicated to theory of atoms, and we hope we have some interesting program for you. So it's a conference that is supported by the general help of Simons Foundation, Bulgarian Ministry of Education and Research, and Bulgarian Research Fund. In fact, it serves as a closing conference for a certain VIHREN project which was supported by Bulgarian Research Fund. So let me give the opportunity to the director of the institute, corresponding member, corresponding member Peter Boyvarenkov, to say a couple of words for the beginning of the conference. Peter?
Thank you. I'm happy and proud to open conference, to see you, to see the conference in the institute. This is maybe not the mathematical title of the conference, our theory of atoms. Some fields started by Kontsevich, Katzarkov, and their collaborators. But I believe that it will become maybe more mathematical than physical in the next years. We're proud to have it supported, and we thank to our supporters, Simons Foundation, as we already said, Bulgarian Ministry of Education and Science via two programs, one scientific programs called PCOM, Enhancing Mathematical Sciences, and VIHREN. Maybe VIHREN is one of the most important in this case. We have our first session, Bulgaria has our first session in this project, large project VIHREN, and our project, the project of the Institute, the project of Ludmil, was the first to start, and it is now going to complete. This conference is the last, okay, not only first in some sense, but also in a sense the last, and to complete the project. And the project seems to be very successful. So there were other projects. In one of them, the team leader became prime minister, and so on. But in our project is going to be completed as supposed, with great success. Okay, let me say again, welcome to the Institute, welcome to the conference. I wish you fruitful conference, fruitful conversations, not only during after the talks, but also in coffee breaks, in your social time in Sofia. The weather is indeed nice, and it seems to support our activity. Okay, thank you very much. And
so this conference takes place in the Center for Mathematical Sciences. It was an idea of academicians Revalsky, Sendov, and Mushkarov, which actually was given a lot of traction by the, once again, the help of Bulgarian Ministry of Science and Education and Simons Foundation. So we hope we have many similar conferences in the future, and hope even more you are our guests, not for the last time. So I would like to give the opportunity to academician Revalsky to say a couple of words, just welcoming you to this center.
I thought that the words of the director are enough to open this conference, because it is really a great success to have such kind of project. It was the first time when this program was opened 5 years ago. Ludmil was one of the persons that proposed this project, and I'm very happy that it was successful, because mathematicians always give example to the others how the things should be done. And I'm happy to see that it is ending also in a very good way with this kind of conference with so many people here that cannot even find a place. It is a conference that ends this period of the project that Ludmil had, but it is also the beginning of something new, because starting from the 1st of January, he will start another project of more or less the same type, but already not in the VIHREN program, the International Center for Mathematical Sciences here, but also supported by Bulgarian government and Simons Foundation. And I hope that the next project will be even more successful than this one. So I wish you a very successful and very fruitful conference, and good stay also in Bulgaria, in Sofia in particular. Thank you.
So before we give opportunity to Max to introduce us to the theory of atoms, let me just say that in this form we are studying it today. It was certainly introduced by Maxim. So now we would like to give different points of view of the theory of atoms. One connected to symplectic geometry and getting variational invariance. One is starting from symplectic geometry and leading to symplectic invariance. And then different interpretations, ones in p-adic form, melodic form, and so on and so on. So there will be different points of view present in talks by Maxim, connection with arithmetic, a little bit more on the A side in the talks by Zabo and Budur, and Muhammad as well. And in the Simon talk, there will be a little bit more on the p-adic side. So we would like to give different perspective of theory of atoms and connection with other subjects. So without any further ado, let's try to make sure that we have a connection with Maxim, who needs to start pretty soon.
conference. Yeah, so I'll just briefly recall theory of atoms, variational invariance from atoms. Yeah, this is the first.
Is it possible to see the screen?
Mark,
Yeah?
can you put the screen on?
It is on, I think.
It is on
What screen?
It's on top.
Oh, it's on top. Okay, it's fine.
Forget. You share the screen. No, you can see on my blackboard.
Yeah,
You see
fine.
it?
Now.
Yeah, okay.
Okay. Good. Yeah, yes, it's variational invariance from atoms. It's something which we are writing now. Ludmil. Tony Pantev, Tony T. It's something to produce variational you can see the variational geometry over C. And the idea is the following. You have a smooth projective variety of dimension m. In my case, it will be n equal 2 or 3. It should be 3. But let's do general story. You get a variety, and then you consider a subspace in the mode of X with complex coefficients. Okay. Spanned by upright classes. If you get just any subspace, then you get a linear subspace. Then you get certain there are two pictures. This kind of ideal picture, this ideal picture, with canonical semi-orthogonal decomposition of the category of perfect complexes, defined up to Ray proof action. So with semi-orthogonal decompositions will be certain usually people make this notation that you get full subcategories, saturated subcategories, so that perfect is semi-orthogonal of this guys, and Brad Hook brings V with L strengths. L with the number of pieces. This is ideal picture. What will be L? L is the following. You consider number of eigenvalues, distinct eigenvalues of multiplication of so-called Euler operator, acting on homology, and Euler operator comes from theory of Bromfield invariance. Theory, it's quantum. If you should imagine us to have some kind of Frobenius manifold, including Bromfield invariance of genus 0, Frobenius manifold, and Frobenius manifold is called homology of X. And now we get this subspace on V. And when you get the subspace, to get the subspace in homology, maybe this should contain all second well, break second homology of X. Yeah, so it gives you submanifold of Frobenius manifold, and there is certain operator operator responsible for the gradient at each point acting on cohomology. And you can see the number of distinct eigenvalues at generic point of this submanifold corresponding to the subspace V. Generic point of submanifold in Frobenius manifold. Is 23. Just for any subspace, you get, if you have larger subspace, you get a larger number of eigenvalues, larger decomposition. Yeah, that's the ideal picture. And it's very far from being rigorously restored, and there are kind of legal tools. One can do some kind of remnants of categories. Yeah, for example, if you use something like Koch cycles, instead of algebraic cycles, and so we will be space generated by cohomology Koch cycles, and instead of replace Ci by what the Auckland homology of Ci, and it will be kind of hot structures. In particular, you get something like filtered vector space over C, maybe super vector space over C. Yeah, if my category is derived category of some submanifold, then I consider homology of this manifold, and HPQ would be into E minus P of integration of maybe beta P minus Q over half. Yeah, okay, yes, that's so you get this plenty of things. It's kind of black box. This atoms, it's general black box, and this is only essentially one tool which I use today. If canonical class affects this non-negative, it will be Calabi-Yau general type. Then number of atoms is 1. Okay, and this cohomology is called cohomology of X. With this hot filtration which I'm talking right now. Okay, yeah, so we use very root part of the whole story, but for convenience, when I will speak later, I will speak about categories, and one can replace categories with the operator invariants. Yeah, this is a story for in partial geometry. I will be interested in equivariant partial geometry. Yeah, so this means we have a group acting on X, and we'll define a group. And in fact, in my talk, will be assumed that G is not only fine, but it's cyclic group of prime order. So it's kind of a really simple group. So what will be, and when I have just before going on, I want to return to this story. You have these atoms, this invariance, and the main part of this story was blow-up formula. Blow-up formula. Maybe I'll take this. If you have variety, it contains some variety Z of dimension A. then what happens with atoms of blow-up of X with center Z will be atoms X plus K minus 2 copies atoms of Z. Yeah, that's the main tool to how to relate theory types with variational geometry. And what you do, how we apply it for some very, very small dimensions. For atoms, we can get control whether it can appear from varieties of small dimensions or not. And that allows to distinguish a variety from the vector space. You cannot move around to us by blocks and blowdowns. Okay, so now we do variational geometry. And in variational geometry, you have group action, then any variational equivalence, G equivalent variational equivalence, its composition of blow-ups at some center, such that this is invariant under group action, it's some submanifold, maybe not connected, in dimension 2, and inverse correct, and blow-ups and blow-downs. So what kind of atoms should we use? The subspace in cohomology, which we are thinking about, will be space, more or less space suspended by algebraic cycles, which have G invariant. Or in our situation, it's the Hodge cycles, which are G invariant. Yeah, so we will see, particularly we see the G invariant part of cohomology. And again, ideal picture. One get canonical SOD of complexes, but as a category endowed with G action. So it means that you get an orthogonal decomposition of categories, and C category Ci invariant on the group G. X or G equivalent. So it's all perfect C. Yeah. Such six gives this associated category like G equivalent shifts, but it's kind of like secondary information. Yeah, so that's now we look on symmetrical exposition with G equivalent, and again legal part. You get filtered spaces, filtered superspaces, endowed with G action. And then one can the same theory of atoms if you look at types of invariants. Okay, that's one story. Now there was another stuff which there's another invariance in equivariant variational geometry, which was introduced a few years ago in a paper with C.D. Pesto, Ruby. Okay, yes, so again, I just assume the group is Z mod P with P is prime. And the invariant is inverted rational invariant in a certain group which depends on J and N, which N is dimension. And this group is generated by symbols, sequences of N characters. And such that not all AI is equal to 0. So there's sequences of characters, which you can imagine like a weight of action of J fixed point, modular relations, and the relations are like this. It's, you consider it's invariant under permutations. The second relation is that for any K N, K will be codimensional variety in a block. It's called K1 K N is equal to sum over I1 to K. And then we take K minus Ti. To keep Ki on its place, then from first K other K elements you just extract AI and then keeps the rest the same. What does more or less mean? You imagine, consider some variety of two-dimensional K given by the last n minus K coordinates in coordinate space, and make blow up, and then we see the weights in this normal bundle. And yeah, so it's some abstract group, and invariant is the following. You consider fixed locus. Yeah, I forgot to say that it's G is, in most situations, G is the action is generically free. Yeah, because you consider this action which is trivial action, then introduced to usual algebraic geometry. Yes. Yeah, so you consider generically free action, and that is, I need this all symbols are not equal to 0, otherwise the action will be trivial in the neighborhood of the point, and then it will be trivial everywhere. Yes, yeah, so it's invariant to the point. It's locus, it's union of some connected components of dimension between 0 and n minus 1, because generically it will be irreducible components or connected components. And in the invariant of x is the action. It will be sum over alpha, and what you do, you consider weights of G action at tangent point with x, where x is any point at x alpha, so fixed point, and it doesn't matter which point you choose or which kind of components, the weight will stay the same. Yeah, and then easy calculation, you just look what how you have some manifold, how log, and you'll see this relation holds. Yeah, yeah, that's kind of like very root invariant. One can make more refined version. Take into account birational types of this apparatus X alpha. In our original story, it was inverted birational type. It was nothing. We keep with birational. We didn't distinguish birational types. We know that this X alpha is connected, and we don't look on more delicate information, but one can develop a little bit more fine story, and it was developed, I think, with VIHREN and Antoine Cheberlois. When we take account birational types of fixed loci. And we get again some invariant. You can check on the blocks result. So there are two different stories. This symbols is geometric and atoms is mysterious. And in general, almost impossible to calculate. And what I want to talk today is about a simple example of some three-dimensional variety. And with cyclic group action, group will be Z mod 3, or we can make other cyclic groups, such that neither from theory of atoms you cannot conclude that the variety is not G-rational. Neither from theory of symbols you cannot conclude that it's not G-rational. But if you combine things together, make blocks, miraculously the whole things prove you that it's not G-rational. Yeah, so it's like really a phenomenon, and maybe it's the only proof of this example up to now. Yeah, so combined invariance. How do you do combined invariance? Yeah, so we can consider group, abelian group, and move out by some relations, and invariance will be the quotient group. In abelian group, we can combined object is it's a free module abelian group generated by many things. Yeah. What are things? Kind of A will be atomic type of generators, atomic generators. And here I will speak about kind of like pairs. Saturated category, P plus G action, and category will be category kind of in this abstract atomic position. Or again, it's a real picture, and legal picture will be pair will be filtered space with G action. Proportion Kamolka instead of category. Yeah, so it will be more convenient to think about categories. And then symbolic part, it will be symbolic part. The symbolic part will be things which you can see from fixed loci, but now I will keep track of birational types. And yeah, so we'll have like this. All A are 0. It corresponds to isolated points. Yeah, sorry, maybe now I will go to dimension 3. So I have isolated points, or I can have things like this. I can have some curve. It will be isolated, it will be a component. So that's this point. Here it's exactly P1. Or it could be curve of curve of genus this one. Or it could be surface up to variational equivalence with some number A1. C is surface, and A1 will be the weight of the action in normal direction. Yeah, so here I get not 3 characters, but smaller number of characters, the rest will be zeros along this submenu. Yeah, so get kind of categories and this kind of geometric data. And then I start to make various blobs. It becomes this data and modular sum related. In the relations, what you do, you consider submanifold invariant on the action group and could be point or curve, maybe not connected, and you make blow up with this curve. And examples of relations. Yeah, I will not write all of them. There are really like about a dozen different types of relations. And yeah, for example, you can imagine you have a point. Then consider orbit of this point. Orbit of this point, and when we make a block, what disappears and what appears. What disappears, it's not fixed point. This is not fixed point here, but after make a block, you replace each things by P2. And still the action will be free. And what happens on the level of these categories? You add category in the semi-orthogonal decomposition. What you add, you get twice category of perfect complexes on Z mod P on a finite set with kind of free the action. I'm so sorry, no, you get not twice. Yes, you get twice in 3-dimensional space. It's 4-dimension -1, and you do nothing with fixed points. Yeah, so this you get this guy is equal to 0, or you can do some uncomplicated stuff. Here, really many relations, and I don't want to bother you with these relations. I will keep track on some portion to this group. You can consider only part of generators and part of relations, namely what will be atomic generators. Atomic generators again, I will speak about categories. It will be respond to the following things. It will be generators respond to classes of categories with action. Yeah. You get category perfect complex on the curve of genus list 1 with trivial G action. And interesting only on such atoms, and because of genus 1 it's it will be really atom on this curve. It's going to classes positive with trivial, yeah, we get with 6 with trivial G action. Again, it's kind of ideal picture and legal picture. You take the Topological curve and make trivial G action and usual Hodge calibration. In this non-sense like P minus Q. Yeah, these are perfect generators, and what are symbolic generators, which you track on the symbolic generators will be the following. You get again X alpha is just a second. You consider your curve, it will be a fixed locus of this mutation, and with true numbers. Or surface, which is bidirectional equivalent curve for P1, is again some number. So we get only such guys. This again curve with bigger than 1. Yeah. So and look in this situation, look what goes on. Yes. I just recall generators. Interesting. Yeah. The curve. This is the curve. Genus. Action. And rational equivalence. Sorry?
She's smooth.
Smooth curve, yeah, okay.
Just to make it
Smooth projective irreducible curve. Okay, what are relations? We can blow up at points and occur in dimension 3. In dimension 3, we can blow up at points or curves, not necessarily connected. And when you blow up at points, this could be an isolated point or orbital point. You don't. These things then never appeared in nothing happens with them. These categories, the categories of points or curves, and then with fixed points you don't get such kind of varieties. Points are irrelevant. So we have to blow up at curves. The curve should be curve of genus at least 1. curve with genus 0, again irrelevant, or genus bigger than 0. And then one can try to look at various situations. So Z will be a free ZP orbit of a curve. We get curve. We get free ZP orbit, and when we make a blow-up, we make the following things. We add a category of C perfect complexes C multiplied by this orbit, Z1P with free Z action, P equals P. P doesn't matter. No. Free action. And you do anything equal to 0, but so that's what happens in the block. But you see that this category, it is not very interesting. We are looking for, because the action of G on homology is non-trivial. So it's, for this three types of generators, it plays absolutely no role. Yeah. So the second, then this implies that Z is a copy of C. We blow up at C. And here there are two versions again. We blow up at C, and one of the situation is the following: is G action on C is generically non-free. It is generically non-trivial. If the action is generically non-trivial, then we have perfect complexes of C with G action, with single P action. But it's again not n plus something for fixed points. Something happens for fixed points. Again, this category is not what we are looking for, because if group acts non-trivially on a curve of genus bigger than 1, and maybe I'll say maybe grid genus bigger than 2, sorry. Yeah, I will go realize it's a little point here, genus greater than 2. And this, the picture gives the group acts on a non-trivial on curve of genus bigger than 2, then text non-trivial on its cohomology. Even for by legal tools, we can distinguish it from what we're interested for. And with fixed points, we will see maybe some block of point, fixed point. You get something related to something rational, not related to curve at all. So it's again irrelevant. Yeah. So then we conclude that G acts trivially on C. But now, again, there are now again two possibilities. Yes, it's C is a component. C is connected component. So it means that and C will be lies in a connected points, but not in connected component. Yeah, so that's essentially two cases, and now I go to next page. Yeah, so just C is connected component or less than connected component, which if you the surfaces. Okay. And only two interesting cases. Cases system component and normal action, normal weights between A1 and 2, or C is system surface, normal weight A1. Yeah, maybe now I just go to here's this. Now assume G is mod 3. That's to be more concrete because here again we get again some two cases. A1 is equal to A2, A1 is not. Yeah, and now I think this geometrically will be different situations. Yeah, so we got three cases. The cases, and now I assume that my G is equal to 3, so this A eval A means that AI is 2, 1, 2. Exclude 0, this is my notation. Yeah, so I got three different situations. Like in the first situation, when I get a curve and two numbers, alpha, 0, 1, 1, our relations. In atomic part, it doesn't matter in which situation we stay, we always add categorical particle components of C with trivial J. This will be it will be always atomic contribution, and then what goes on with symbols. And with symbols, we have in the first case the following. What disappears? It disappears the curve with normal weights, say 1, 1. If AI is equal to 1, and what it adds, and what appears curve multiplied by P1, or actually it's P1 bundle, but preparation is curve multiplied by P1, or maybe it is sort of like a P1 bundle of a curve, and with normal weight 1. Yeah, essentially it's like a curve multiplied by two-dimensional bundle with the same weight, and if you make block the weight 6, or it could be weight 2. Or what it could be, yeah, it was KC1, or it could be C12, because if two different weights, V1 and 2, and then what I add, I get C, instead of one copy of curve as fixed locus on the block, I will have two copies, and normal weights will be C11, C2. And the last story, when curve sits in a surface, what I add to my curve A could be, A1 could be 1 or 2, and what I add, I think my curve is always weight A minus A, so you add the curve, so weights 1, 2. Okay. Yeah, so here it is, so we get and it's secretly A1, say 1.
What CV?
Oh, this second. Yeah, you get the curve. It will be new Categorical. It will automatically normal weights will be 1 and 2. Okay. Yeah, so get slash gadget. And now I want to make it like homomorphism to integers, which get some kind of which number, which vanishes in all these relations. Non-trivial homomorphism T. And when I make non-trivial homomorphism to zero, I say, for example, I do C1, 2 goes to 1. Or maybe let's have this. Maybe C1, 2. Yeah, C1 half goes to 1. Then the perfect plexus of seeds trivial J action goes to -1. Yeah, this plus this could be equal to 1, to 0. You get the universal atomic part, and this last example, the curve seeds. Here's situations that get surface, get curve of its locus, and we make this. Well, that's the last equation. Guarantees the 6 looks now. What else? Where should map C11 and C22? You should map to the point the sum of two guys, -1. Okay, -1 is equal to 0. They also map to 1. Then we guarantee the third relation. And finally, for the first relation, in second relation, C cross P, or maybe P1 bundle over C, this way it's 1 or 2, or 2. Guarantees the first relation. Yeah, so one can arrange weights such that weights for each relation is 0. Okay. Yeah, so get some invariant. Example of variety. You do you consider the following guy. Consider some variety in affine space, where P is a polynomial. Degree so connect maybe reaches 3. Yeah, sufficiently large solution. Sorry. It's not like this. I consider let's say x1, x2, x3 will be variable, and you write yeah, you do the following. You consider, let's say, Categorical curve, or any curve of genus bigger than 2, and then you add x to 3 variables, and let's say product of 3 variables will be some section or some line bundle, whatever, and cyclic group action. We will remove x1, x2, x3. Oh, just sorry, I am missing these things. Sorry, I am missing things. So. Yeah, consider polynomial, and what you get a fixed locus, get kind of like the generalization of hyperempty curve, and if polynomial has of degree at least 2 with simple roots, then the fixed locus is a curve of genus plus 2, and then we can compactify this guy to infinity, make a smooth projective variety, and no more fixed points. Or fixed points. Yeah, so we get this curve of genus bigger than 2, normal weights will be 1, 2. Okay, so we get a category to symbolic invariant curve with 1, 2. Okay, and atomically you do you get nothing. Nothing, please, for these invariants which are interested. The reason is the point. This variety is obviously rational. Forget about G action, because you can extract variable x1. Variety is rational, and it's cohomology. If you do computation, all cohomology are Hodge cycles. It's driven by algebraic cycles. There's no traces of cohomology of C in the cohomology of this variety at all. The curve sits in the variety, but homologically is not here, and the category, and you cannot have HPQ is equal to 0 for not used. So we cannot have whatever atoms we are looking for. This specific atoms with equivalence equal to 0 is not okay. And then the invariant is 1. And then if you check the projective space with this reaction, linear this reaction, it's 0, so it implies it's non-trivial, non-irrational. Yeah, it's all very nice, but now if I look on these examples, let's go back to these examples. We have these relations, and suppose we ignore one of series, for example, ignore series of symbols. Then this verb G with trivial action can appear as a new atom from nothing. Yeah, if you have a surface, some surface, on the surface you draw your curve. Surface could be P2, but on the surface you can draw a more complete curve, make blow up, and then you add to your atoms this perfect of categories trivial action. So you cannot distinguish these things from trivial or not, from rational or not. If you ignore a series of atoms, then you see C12 is equal to 0. Yeah, so it's again things you cannot distinguish. Yeah, but only combining tone knowledge together, you see that this thing exists, and it's pretty amazing phenomena. Yeah, it's one can replace Z03 by other cyclic groups. One can do something more. I'll just say it orally. And theory of symbols, when we refined, we look on birational types of fixed loci. One can try to look on more complicated data. Non-birational types of fixed loci, not only of degrees of normal bundles, but actually non-birational types of actual geometry of fixed loci. So it will be actual surfaces of and also one can look of degrees of normal bundle of weight components of the normal bundle. Yeah, it's already very complicated story in dimension 3. We didn't check it out. We try to work out the story in dimension 2. When you look on for fixed loci, I look at degree of normal bundles. For dimension 2, you get surfaces. Let me blow out its point, but fixed loci are curves. And let's just take it. One can develop very refined function of symbol groups, taking into account some actual varieties and with normal bundle, G equivalent normal bundle. Yeah, that's make this delicate story clear proof non-rationality in this my stupid example without going to this mysterious series of atoms. But already in dimensions 2, get kind of new would be and B into G kind of fine. And it's really different, and for G's cyclic group, but now let's say P is 5. The rank rational rank of B to G. It's kind of funny number which we calculated, or at least experimentally calculated these examples, and rank of B to prime. We can take into account degrees. This will be slightly large number. One can work out it. Here actually the book is very funny. You get group generated by symbols A1, A2, A1, A2. A1. Both knowledge to zero modular relations. There's symmetric. And modular another relations at A1, A2. A1 is minus 1. A1 minus 2 equals A1 and A2 0. Yeah, so it's slightly different relations. You consider only non-zero weights, and that computer experiment shows that you get slightly larger dimension. But I'm not sure. But in 3 dimensions, it's completely nightmare. We get to invite the whole situation, and I don't know whether it's will restore pure geometric proof on non-general rank. Thank you.
Thank you.
Did I give a talk to anybody?
Yes, you did.
Question?
Did, yeah, but not to.
No, I think they heard it, otherwise you would get a call.
I got a call. I think it's this like some part of the speech is.
They're so impressed that they're
Yeah.
Any
My
questions?
speech at least exists in Bulgaria. Yeah.
Yes.
Hello.
I think I know what a symbol is, like, but I still don't know what an atom is.
Well,
Sorry?
you're not alone, but in any case, so there will be more coming on the theory of.
Can you hear us at all, or?
He's
standing from that. Yeah.
Max, can you hear?
Yes, I hear. Yeah. Fine, yeah. Yeah.
Questions? More questions? So let me just say that as the conference goes along, there will be more introduction of the material. There will be talk by Leo, then by Tony, and then by Mohammed on Tuesday. And there was a request. It makes sense to have a little bit of office hours, maybe on Wednesday after Mohammed talks, where you can ask me, Tony, or Mohammed, or Leo questions about the theory. But before Mohammed talks, probably there's not much sense after that.
Maybe we can ask, is one of these CIs, is that an atom?
Well, CI, actually the causal homology of this is an atom.
Okay.
Other questions? Well, if not, let's thank Max again. So we continue in 6 minutes.
Sorry for being over time.
Sorry, I apologize. In 11 minutes we'll talk. In 11 minutes we'll talk by. So let me introduce Leonardo Cavenaghi from Campinas, who is going to tell us about or thin round atoms or free atoms. Leonardo.
So first I'd like to thank very much the opportunity to be here. Given these last questions during this talk, I decided to spend a bit more time on this atom subject. I must say that this was not that prepared, so please forgive me. I will try to give some insights. But the title of my talk is the word free atoms, such as we have the pre-Socratic philosophers. So before the light, you have to deal with some noise, and constructing on this noise, I'll try to motivate atoms from my perspective. I was not there when it was founded, but I'm more or less trying to appropriate it to myself and put in the way that I try to understand, and I hope that this may enlighten you a bit. And the way that I like to tell this story is very, very much influenced by a guy named Hiroshi Ritani, that many of you may like, and I think I read all of his papers, and especially the surface, that I think is quite outstanding. And to begin, and here we are mostly looking to X that shall be smooth, projected. Right. Always over C. And then I recall to you that we can think about the small quantum homology group as this family of commutative products on this homology. And here I'll also take this on this homology. And at least to my understanding, the atom theory starts like much later, what is named like much earlier, of this K equivalence, or if you like also some kind of frequent conjecture.
Sorry, is O tau supposed to be the quantum product?
Yeah, so this is the small quantum product. Sorry. The small, that's why it's like circ.
Okay, sure.
Sorry. And I recall to you the following sentence, folks. If you have then two small projective varieties, and you suppose that they are like in a bidirectionally equivalence relation, okay, then I'll also ask the following, that I'll say that they're like in a frequent relation. If we can find, let's move it. If we can find a third smooth projective variety here, and variational morphisms. So let's say that the map that gives us there are these maps and X tilde, and such that when you pull back the canonical classes of AX1, it coincides with the pullback of the canonical class of X2. This is here in what I'll call frequent in general. Okay, then I have two projective variational varieties. Then I have projective morphism. I'll say that they are like in a frequent relationship. If I can find a third smooth projective variety X tilde, and the variational morphism such that when you pull back the canonical class they coincide. Then, what is this real unscrapant conjecture? Is that if we look to the quantum homologies of small quantum homology of X and Y, they should be isomorphic under some, then there is the big part, analytic continuation. On the parameter spaces. Okay, so the quantum homology rings, small quantum homology rings, they should be related by some kind of analytic continuation. But to this, like in general, what physicists would expect is that if you build this, let's say, quantum D model, and I'll explain this more or less in the context of the stacks soon enough, then you would exist. So buy this picture for a minute, and then the details are out in a moment. It's like you can embed what Maxime called this kind of Frobenius manifolds in some huge Caehler modular space. So this is going to be something that I'll call P1, that will be related to X1. This will be something that I'll call P2. And let me tell you for the moment that these are formal neighborhoods, these P1 and P2, where the small quantum product for the quantum multiplication here converges. It's like in general, this may not exist. This is an issue also with these people to develop atom theory had to circumvent. And they did this by extending this notion of F-values. So for now, buy this picture for a moment that we have V1, that's a formal neighborhood where the small quantum product converges for the quantum homology of X1, and this the same for X2. And then the idea to promote this analytic continuation is embed everything in some huge Caehler modular space. And then the analytic continuation of these parameters would be done in this space by the means of choosing paths. So you have then your parameters here, you had some curves showing them, or some weaker versions of this is like you make this small Frobenius all along this huge space, and then you can more or less try to understand as you are doing quantum deformations to get these parameters. But this is K equivalence, and it's very important to look that this is a relation about the joining, meaning choosing paths to connect quantum multiplication. So these isomorphism under this kind of analytic continuation depends pretty much on the product. That's the very important thing. But this is one part of the story. This is the equivalence. There's no atoms so far. But you also may remember that Maxime says something about some kind of blow-up formula. And that's the thing that we change now to go on to motivate, because okay, this K equivalence or equivalent relation can be a bit tricky to exist in general, and sounds like quite restrictive. For instance, this is related to Mackay correspondence or Ernesto. Renato Henrique has also some works on this direction, but one way to like make this a little bit like slighter. In the following sense, instead of asking, so let's call this then, instead of a perfunt, we put this perfunt, and then we put in a this perfunt relation. If instead now, this should be less such as that, instead of this isomorphism, I'll ask that the difference in the pullback is an effective divisor. So this is an effective divisor.
Can I ask a question?
Yeah, of course.
So in the original statement, is it that if you choose a given x tilde, that corresponds to a choice of path in this, up to some...
Yes, this is true. This is true. And there are many issues with this approach because there are many choices and also this path they can carry some monodromy, but this is true. Different choice of this model should lead to this. This is true. To difference on this huge Caehler on the space. Yeah, sure.
So McLean proved some version of this conjecture. I'm sorry, I mean, I know this is going to be this long.
Don't worry.
Since you read all of Ronnie's papers, I thought I might as well ask. There's some version of this conjecture that's proven when x1 and x2 is Calabi-Yau, but it's phrased in a different way.
Yeah.
Did anyone have to figure out how to relate these phrasings?
In which sense do you ask this?
Well, there's the statement that they're isomorphic after you change the Nada coverings cleverly. So there's a statement that if you have two birational Calabi-Yaus and small quantum cohomologies are isomorphic after you cleverly mess with the Nada covering. You know, this is some kind of replacement for analytic continuation. Does anyone ever who thinks about this stuff ever understand how that fits together, given that no one ever succeeded in proving Ron's conjecture in general, in that kind of stuff in different language?
I mean, I'm not claiming like such a huge expert, but I can tell to you maybe if I properly understood your question. In this discrepant case situation, there is this block formula we're going to talk about, and when you restrict to K equivalence, you can, or discrepant or equivalent transformations, you can recover this. And this is like properly done by change of variable formula, and this is also reflected on this kind of motivic integration. But I'm not sure if I fully understood.
Okay, that's fine.
But let me tell you something. When you do this atom theory, you can prove this Kontsevich mirror symmetry first theorem for Calabi-Yaus because they will only have one atom mass. You go to this AX in greater than 0. But I'll get there at some point. Maybe I didn't understand you. But okay, so you have then the difference is like an effective divisor, okay? And a simple example of this is like what you do. If you take then a smooth superright Z on X 2, for instance, and you say that R is the coordination of Z in X2, and you assume as 0, then you do the blow up. This is an example of a discrepant relation. And then we know that the homologies, standard and singular homologies, this guy.
So what is this R set or what is this R2?
Yeah. So R is the coordination of the Z in X2, and this is greater or equal to 2. Then additively, there is this blow-up formula relating the homologies. So we're going to have X plus R minus 1, right? This is very classical. And then you see that in a discrepant relation, such as blow-up, if you like, the ranks of the homologies are different. So you cannot expect that a conjecture such as alpha ones hold in this context. You have to fix this. And what would be then more or less natural to state as some kind of Ruan's conjecture in this setting? So in a discrepant relationship, such that this difference then is an effective divisor, you ask that instead of isomorphic under this kind of analytic configuration, this guy here is a direct summand. Contains this as direct summand. Okay, just to, that's more or less natural is the way that you fix this discrepant Ruan's conjecture. It just as that. And then it comes in terms. And what we can do? It does the following. You have this formula that's, I said, that's additive. You have some kind of like one discrepant conjecture. Then how can you relate, how can you prove such a thing that, for this case? And he proved this for blow-up. So, VIHREN is a blow-up version, let's say, of one discrepant conjecture.
So this containing there some up to some isomorphism.
Yeah, under this kind of analytic continuation again.
Because if you have a usual variety and make flops, the usual Karamoti doesn't contain in the sum by.
Yes, that's completely true. Indeed, this is something. And here again we are in this picture that we have again this huge Caehler model space, and they do some kind of analytic continuation, and it's up to this kind of analytic continuation. But there's some issues indeed, and some strong requirements that people ask. But VIHREN's theorem is like it's proved in quite generality, and I'll state this now. Is this more or less? Yeah. So what VIHREN shows then is that if you pick this, the homology of the blow-up, and then you look to this now B quantum product, then you prove that this is isomorphic. So X now tilde plus it proves that the quantum homology of the B quantum homology of the blow-up, it can be related with the homology of the variety and with the center by a change of variable now. And to do this, he puts everything in like a huge node called ring and do this invertible change of variable. So you pick the parameters, say tau tilde, and then there's like an invertible change of variable formula that's given by this. Tau tilde, and then this. This is the way that to attack this proof, he has avoided this huge Caehler model space. What he do is instead like construct some special kind of called ring to like where to deal with all these quantities, all these quantum parameters all at the same time, and then prove an invertible change of variable formula to prove the isomorphism between these homologies. So this, for instance, concretely verifies what I call by one discrepant conjecture for blow-ups. Okay? But so, what this has to do with atoms in general, right? Why am I like spending time to talk about this? And once more, again, this is like the way that I see the picture, right? You are the dark area, myself. And the main point is that we have then some neighborhood here. I'll call this. So this is one X, where I'm taking these quantum parameters. And I'll make also the very most naive model of this kind of F bundles. Here I assume that this U is like formal neighborhood. Where the quantum, say, small quantum multiplication converges. that could be empty, why not? And as this kind of Frobenius manifold that you can do, so you pick this from our neighborhood, then you transferize with C, or like if you were doing things carefully, some formal neighborhood, some formal disk, then we make this trivial bundle here. That's holomorphic reflect vector bundle. And in general, this is what we call this bundle. That's what I'm going to add here with further structures. And nicely, it carries some compatible connection. Maybe you guys have seen this, like Dubrovin connection. I suppose that many of you have seen this. And there is this distinguished vector field that's like that's the oscillation. That's the other vector field. Having such a story, when you have blow-up formula, then given a structure such as this, you do the same for the blow-up. Once you have irritated blow-up formula, you can relate these bundles and the connections by the means of the blow-up formula, because now you know how quantum multiplication works, and then I tell you that this NABLA connection like encapsulates quantum multiplication and also this order vector field. So once you know Irrita's blow-up formula, you can relate these bundles with distinguished connection and order vector field both on X and also on the blow-up. Okay, so this is like why it matters, is Irrita's blow-up formula. And again, I like oversimplifying many stuff also, and assuming this kind of convergence. Atom theory is like made to bundles such as this, but without convergence issues by choosing the field appropriately. So like, no like median, whatever. And I'm sure that 2020 will give many more details in a many more expert way than I am tomorrow. So you construct these guys, and now you may ask, can you please define atoms, right? So I suppose. And so let's make the first definition. You have this Euler vector field. I recall to you that some part of like the Euler vector field you can write as, or think at least in computational terms as this, where we have here. So this is the small multiplication, this is the furniture sharing class of the different bundle, and this other vector field here, it will act on the fibers of this bundle. And you can really see this like endomorphism of the cohomology to the cohomology itself. So there's a matrix. And a matrix that turns out to be diagonalizable. So this, like you can see, is endomorphism. And then I said to you that this is diagonalizable. If you pick then a spectrum of this guy, the quantum multiplication here, you have some lambdas. And consider the eigenspaces, right, for this decomposition. blank space. So that's how it is. This is bad. Let's put symbol.
Each star means quantum homology.
Well, small quantum homology.
Yes, small.
Yes. And of course the C1 here. You decompose this, and I'll call the species. These are some local. The pieces in this splitting, I'll call these local atoms. Why I'm calling local atoms and why I'm being more or less vague here? Because if you put additional structure on the quantum homology, and I know that Tony is going to do this tomorrow, then you can get many different notions of atoms that depend on these additional structures. This is, as I said, the pre-Socratic world. This is like a toy model for atoms story. But in the end, the atoms shall be like always like this. You know, like when you do mathematics, then you also have to have one example in your mind. To always like goes back to this example. This is my example. It's like very cumbersome atoms in general, but if you assume that you have this quantum convergence, you do this bundle, like assuming the convergence, you look to the Dubrovin connection, you look to this Euler vector field, but more like naively, this C1 with the small quantum product, it acts on homology, it splits pieces, it's splitting pieces. These pieces given by this splitting is what's called like local atoms. And then yes, sure.
So what kind of an object is an atom? I mean, pure is just a vector space?
No. Indeed, this is the point. So you can always choose this base for this Frobenius manifold here. For instance, I choose where the quantum product converges. But instead of dealing with the full quantum homology ring, I could restrict myself to the algebraic part of the homology and then restrict to the quantum product there. And then the species that coming from this splitting, that are not only vector space, they carry with themselves also, for instance, Hodge structure, the algebraic cycles as well. So everything passes according to the choice of this kind of bundles that you pick. And that's related to what I said about like there are many notion of atoms. If you put more structure, then you can like get more stuff. But the main spirit is these decomposition are not only vector space, but you expect to recognize them as pieces of homologies of other stuff. For instance, one of these V lambda could be some piece of the homology on a curve or a surface. And to do that in small dimensions, you must be able to recognize what are these pieces. So if you have Hodge structure, you can relate them to Hodge diamonds and try to figure out to which stuff this belongs.
So I guess to put the question differently, are they objects in some category? And do you know what category that is?
No, atoms doesn't form a category in general.
Special objects in some larger category? Or?
I don't think this is no.
Pranav, it's bad with morphisms, so it's not.
Sorry?
Morphisms are not well defined.
Yeah. But for instance, there is something that I'm not pretending that I understand, just a secondary answer, of course. But if you have some bundle, for instance, then when you write this, write category. I write this like this. Let's say degree B. When you write this semicolon decomposition, of course you have these braid actions and everything, but you expect that the eigenvalue at 0 corresponds to the component, like of some identification. And if you take Hodge homology of this guy, you expect that this is really 0. And the other exceptional collections come from the other eigenvalues that are not the 0. You see, there is like a clear relation with this derived category of coherent sheaves. If you see, for instance, this component, you take the Hodge homology, you can identify this with the V0 with the eigenspace at 0.
But the other pieces of the exceptional collection is the composition of EV into generators of the exceptional. What if EV has infinite image? It doesn't have an exception.
Well, so this is like a bounded
Topological.
Oh, bounded.
Yeah.
I forget.
Yeah, bounded derived category, yeah. And of course, I'm not saying this is unique. For instance, there are all these gamma conjecture story that try to make a proper sense of how to relate these pieces with the semi-economic composition. But again, I'm not an expert on this. I'm not pretending I am.
But Maxime did mention, though, that there is this kind of ideal picture. There is not legal, then there is the legal picture.
Yeah.
And while the ideal picture is not legal, what is the ideal functoriality of the story?
Well, you have functors, but in order to get some uniqueness, you need to invoke some stability conditions, and then I don't know how to choose a component of stability condition.
For instance, maybe out of the following sentence. You saw this blow-up formula on 3D time, right? What this could do is that if you do some kind of blow-up, then you have these eigenspaces, and they're putting together different eigenspaces, like coming from instance from center. So like when you do the blow-up formula, then you collect these eigenvalues, and in the blow-up you may have some new contributions to the eigenspace for that eigenvalue coming from stuff of a dimension greater or equal than 2. So to decide whether you can split these pieces and recognize if they belong indeed to some kind of like minimal stuff where the pieces cannot be further split. And I think this is why atoms, because you want to get some kind of minimal decomposition and recognize that these pieces in this homology doesn't come by patching together these new eigenvalues on the blow-up by Newton's formula. Then you need to have this kind of stability conditions to decide whether these things split further or not.
But let me just ask, again, a very naive question, extremely naive question, but this, of course, these Frobenius manifolds are variations on topological quantum field theories.
I don't know this.
It's just a family of topological quantum field theories. And topological quantum field theories could be construed in the Lurie picture and many other possible foundations as representations of categories, some sorts of representations of categories. So it feels that perhaps too naively that the possible functoriality that we will be talking about here is that because they behave like representations of categories on other categories, of course, if it's an infinite categorical picture, the functoriality is that, it's like a representation ring functoriality, like a K-theory functoriality for representations of these categories. So this even makes sense, or?
Maybe someday, but at the moment we don't know.
But I mean, what I want to pass the information from today is like, this is a theory where we have to rely on quantum multiplication to provide some splits in cohomology. And these splits in cohomology should be compatible with any kind of structure that you put on a cohomology, in algebraic cycles, Hodge classes, and everything. This would pass from the extent to the decomposition. And there's a clear parallel here with the derived category that's like yet to be understood in many ways. And why you would say then like local atoms is because then you can go beyond this and define what it means like atoms or fields, and that's why they can deal with rational problems. But this all amounts to the fact that you have a blow-up formula and you have these models where we can like relate these Frobenius manifolds, F bundles, undergo. One tricky part is to decide whether these components here that appear, these V lambdas that are not only like vector space but have homology structure indeed, groups of homology, they belong to which varieties. So in dimension 3 and 4, more or less you can work with, but higher dimension can be tricky to try to understand because why dimension 3 and 4? Because you have a minimal model problem for surface. So you can match these pictures and then try to look to the homologies. Greater dimensions starts to become trickier and trickier because you must be able to do a computation and recognize these as species in homology of some stuff that you understand. But this is like the initial picture, and I just said that I started motivating this by this kind of K equivalence, this question about Calabi-Yau also, and the main point is that when you have such a blow-up formula, then you can reduce to the equivalent case because you don't have these discrepancies coming, and then you can verify many stuff. And this is like the initial picture of atoms could be like in very pedestrian way. This was not prepared today, but since the question decided, and may I'll add some small comments now on what it was supposed to be my talk, maybe, and then. But so any kind of other divagation and like question and philosophical interpretation, we can try to comments, criticism.
I'm still not sure what kind of an object an atom is supposed to be.
It's a piece in is like a decomposition in homology that carries some structure. So it's a homology group.
Intrinsically, what is it? I mean, if I'm given a vector space, I can decompose it in some way.
Well, it passes with also Hodge structure, so if you consider algebraic cycles and Hodge classes, then this species comes also graded with this kind of Hodge structures on it.
So it's a non-commutative Hodge structure?
Yes, it is.
Non-commutative Hodge structure.
So atoms are special non-commutative Hodge structures?
Sorry?
Is it correct to say atoms are certain special non-commutative Hodge structures?
Yes, obtained by compatible on the p side with the splitting of the homology and the action of the manifold table.
This is, I know that Tony will elaborate on this.
Yeah, so these are special, I mean, motives was the buzzword of the 80s and 90s that we used to call these things, like in quantum sense. So are you basically saying that this is some kind of special motivic decomposition controlled by momentum theory? Is that?
I'm not sure only about the word motivic, but I remember Maxine said to me that this is not motivic at all. But I wouldn't say.
Everything you say makes it sound like it's motivic. I mean, it's whole structure has pieces that you recognize.
Motives are category, atoms are not. No more.
Okay, but morally at least.
Morally, yes.
Yeah, I mean, I try to understand this like morally in this picture, but there is no commutative Hodge structure, and this guy here also comes from this exponential type decomposition for flat section, blah, 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 that you have with non-commutative Hodge theory. So this is like a big picture, sure?
So actually related to exponential type. So like, if you have this quantum D module, it may or may not be exponential type. So do motives make sense? Do you need to know that the quantum D module is of exponential type for this whole decomposition to make sense?
You don't, and in fact, if they are not of exponential type, that gives you another abstraction to rationality as well.
You get different invariants.
So there is somewhere in some document, somebody has defined this decomposition to some degree, and it does not require that.
Yeah. So okay. Tony will talk about it more over the language of F bundles, but of course, that's the way it's done, and this exponentiality is based on.
Great, thanks.
Sure.
What is the meaning that elements of the spectrum of some eigenvalue values?
Are what, sorry?
Eigenvalues, the lambdas.
No, it's because indeed you have a quantum multiplication acting in this, and you can see it as like morally as linear transformations. But this shall be like a Higgs field, and then you have a spectral cover, and blah blah blah. And Tony will give details on this, but is this like you can really think as like a map from homology to homology, and you can think this like some kind of linear transformation. Everything's like finite dimensional. Then you just diagonalize them, the matrix, and then you look to the eigenspaces for this. It's just this. But this, like in the context of F bundles, you'll see that the Euler vector field is nothing but a Higgs field.
Do characteristic polynomials, do they behave like zeta function kind of thing?
This is something that maybe Ludmil could say better because I don't know much, but I mean, we asked this question to ourselves and we don't know much, to be honest. But maybe it's
No, and there is a different spectrum which behaves more like that, but you just need to restrict to this alpha, and then that gives you something that looks like the Stimbring spectrum associated with singularity, and then indeed your question about zeta function makes perfect sense. But,
in the static case, right? I'll add one comment on this in a moment.
So these notations should be the spectrum of an operator, not spectrum of a ring, right?
Yeah, the spectrum of operator. Here is the C1 Tx with the quantum multiplication. So that, yeah, so sorry. It was my handwriting, like handwriting. But let's add some comments on this kind of to go to the top of my talk and then finish. Let me add the following information. All this story, even this naive story, can be done in the context of stacks. But then the replacement in the homology that we have is not the standard homology, but the chain one homology. And chain one homology? Yeah. So let's add more comments about this and also about the liquidians. That in the end it was not used at all. But so everything in this picture could be passed to another problems and another objects to say, instead of dealing with varieties, we could deal with stacks and replace the homology verbatim. So instead of dealing them, now we pass from X, we're going to look for some dealing for stacks, but more generally, more particularly, stacks of this form, where G is a finite group of the individuals of Y is projective. And the action in the same context as Maxime is the G action is generated free. Okay, and then we replace what's named Schroeder moment that I recall to you that as vector space. So let's put this C vector space. This is the summation So to each element on the group, you look to the fixed point set for this element on the action, and then you look to the action of the centralizer in homology. This is like a C vector space, what's named Chamber homology. What is how is this different from standard orbifold homology? It's because it has like a funny gradient that comes from actions of weights of representation of these local stabilizers on the tangent space. The same characters as Maxime, if you like. And but closely related, let's say, and it has a cup product that is inherited from Gromov-Witten theory, like for algebraic or symplectic objects. So you have this guy, and then we can let's say do the same story here. Right? So you now consider chain 1 instead, and you make this a bit more calligraphic. And then this we keep. And you can do the same story and try to build atoms in this context the same way. So like this naive model that you want to do. And the first step to work this out would be, of course, to have a blow-up formula. But even like for chain local models, and this we do have. So let's say that we have a blow-up formula. For this guy, or and once we have this blow-up formula, we can mimic these atoms, we store it in the same way. But they are trying to do it with like rationality questions. What does mean a stack or something like this to be rational? Well, it means nothing, of course, because you don't have projective space. But you can, if you have given two stacks, then again, it's the same story. I can find another, and then projective now, operational morphisms. Two stacks are variational. If you have this, two stacks are variational if they can be put in a relation like this, where sigma, tau, and phi are projective operational morphisms. You say that these are stacks in a equivalent or discrepant whatever relation. You can mimic and say that they are like in a equivalent relation if you pull back the canonical class of the stacks to this correspondence space, and they would be related, like homology. And with this blow-up formula for chain rule homology, we can show that, for instance, we can show that if x1 is variationally equivalent in this sense as stacks, and we have they are in a equivalent relationship, then their chain homology rings are isomorphic. But moreover, for discrepants, we have that. So if
one of them is a tau.
Sorry?
One of them is a tau star, I guess. On the right hand side, it's a tau star, isn't it?
Tau star? Yeah, sorry. Yes, very sorry. Yes, sure. Yeah, sure. Thank you so much. And if this guy here is effective, so let's go like this. I mean, that's effective. They differ by like effective divisor. And this guy is a direct. And this is the baby steps of atom theory for stacks. This kind of relations. This is some kind of like a returning story, but without avoiding these analytic continuations and everything, because this is just sheer local product. But still, it carries Gromov-Witten invariance, Gromov-Witten aspect on it. So if the handwriting is like two words, please let me know. Is a direct summary. And just to finish, and like to say that once this is all like put, I see this is like an opportunity to try to find new relations between old stuff in general. And related to the question about this characteristics of the functions and etc., I must only add one more to this. And the expectation is that with the emergence of atomic theory, we can better understand these relations. But what I can say to you is that there is this notion, there is the notion of what is named and in the context of this move, So for compact complex manifolds, this is a multiplicative genus that comes from this word string to any Q commutative algebra. I love that. It's a Q. Oops, sorry, Q commutative algebra. This is like a multiplicative genus with the property that it's zero on the projectivization. So this is some kind of vector bundle, complex one plus x. This is even dimensional. In general, is the notion of elliptic genus by Roshanini, but it can be made quite explicit in many situations by the use of here's a group. If you have your variety, or like a smooth compact complex manifold, and you look to some vector bundle over it, then you know that the other characteristic of this vector bundle is the integration of a chain character, the product of the third class of the tangent bundle, right? In the static case, in the chain homology case, you have analogous Czerny character, and you have analogous third classes. Now looking to vector bundles over orbifolds, right? So like ellipsis taxes, algebraic orbifolds. Then, so elliptic genus, like in this smooth case, elliptic genus, let's say two variables. Is a specific choice of this vector bundle V that depends on two parameters. So Y and Q. Q shall be where this tau is what people call like the Bulgaria parameter, and this Y is 2 pi square minus 1c. So tau belongs to the, let's see, is a complex number where the imaginary part is positive. See. And then the elliptic genus of x, y, and q. This is nothing but the other characteristic of an appropriate choice of this vector bundle. Let's put this. And when you make this parameters q equals to 0, this is nothing but the Caehler genus of here. So it contains many informations. And everything like this holds in the stack context as well. And once we have a blow-up formula for general homology, we have a blow-up formula for elliptic genus. And of course, and then the question is, like, how much the elliptic genus perceives the theory of atoms? And in the case of hypersurface singularities, when you go to the projectivization, specializing at the cube to 0, you get the generated function of the spectrum of singularity as necessary.
Why do you expect that the elliptic genus has anything to do with quantum homology in this setting?
In the static contest,
In any
I expect because of, let's say, vaguely.
Okay.
Because of
some computation.
Frankel-Chesney theorem that the P-genus is the partition function for general homology.
Okay.
Reasonable enough, or?
That's totally reasonable.
Absolutely reasonable?
And this, yeah, if that's the case, you can.
That's the case. And then we know one formula, and then we expect to understand how the genus relates to atoms, and maybe see whether this leads to better invariance to who knows whatever, and maybe in my tomorrow's talk, you're gonna see some taste of this. And then again, I just want to finish saying this is like the pre-Socratic guy speaking. Tomorrow the light shall come. Thank you very much.
Questions? More questions?
Yeah. So you discussed the relation between, say, quantum homology of variety of its blow-ups and so on. Did you consider quantified transition when you degenerate, make a singularity, make a crescent resolution? Because there are formulas in some cases for Prismanic, how quantum homologies are related. They are specified.
This is like a really ongoing project at this very moment, so we'll see. We don't know yet much, but Linus talk will talk about log transforms in some context that will be related to this as well. But it's to be seen.
Other questions?
When you say a block formula for chain one homology, you mean quantum homology, chain one quantum homology?
Cup product indeed, but it is
small quantum product, or
no, it's the chain one cup product, but it's multiplicative formula again. But no, it's the cup product for chain one. Is that clear?
So it's the analog of so Iridani's formula would be a special case of that?
No, I don't think so, because it deals with big quantum products.
So that was my question.
No, the answer is no, not particular case, not at all.
All right. So let's thank Leonardo again. So we continue with talk by Lino Grama at 2:30 p.m. So there is lunch at, on the third floor at 378. So we go this way and go down on the third floor. So you can have discussions there, or if there is no space, the room up here on 503 on the fifth floor is open for discussion as well. See you at 2:30. So lunch is in 378.
The radical is not priced.
I see.
But it's possible.
Yeah.
Because it is basic, it is not. It is not.
I think basic, there should be variety of
Yes, yes. And, you have to specifically choose spicy factor.
Yeah.
It's the southern China that is spicy.
Actually.
Anyway, absolutely important thing is that James since I was in Hong Kong, tea country. In Shanghai, for example, it was hard to find coffee. Now, China is one of the big, huge coffee.
The University of Campinas, and he'll be speaking about spherical T-dualities in the Islock transform on homotopy methods. You know?
Okay, thank you for kind introduction, and I thank the organizers for inviting me to be here in Sofia in this now cold weather, but it's very nice. And today our topic is about the spherical T-duality and generalized log transfer in homomorphic manifold. This is a joint work with Leonardo and Ludmil, and I hope that then we explain how to disconnect with these talks in the morning, or how it is developed and how it becomes part of the program, because this is a kind of before this talk of you this morning, but there is a kind of connection, but it's not, you just can see this posteriori. I try to explain this, start to explain, and we can consider this talk in two parts, and this is the first part, and Leonardo will finish the work tomorrow in the second part, but it's the same thing. Okay, and then we start from the beginning, and just to recall this SYZ approach to reversibility is a duality between Todos federation. Okay, we start with the pair of the Calabi-Alps and Lagrangian federation. Okay, and we say this pair is a mirror if this fiber are dual claw. And as a consequence, we can Lagrangian sections of the one foundation should correspond to multiplying bundles on the another side. This is between the complex and symmetric. But I'm interested in a different approach for T-duality, introduced for Goldman, Hammond, and Matai. T-duality for a principal Taurus bundle with the H flux. And they prove several properties of this T-dual manifolds in this context. I will show the definition in a second. At the topological level. And the intuitive idea behind this is exchange the charge and the H flux. Exchange the curvature in two forms, the principal bundle with the jet. Two forms. And this is a definition. We start with a pair, E and E hat. Principal bundle over the same base. Double bundle over the same base. And then we consider the product space. These are also fiber over the same base. And then we pick two tree forms, H and H hat. Close the tree forms, invariant on the fiber. And we will say that these two pairs are T-dual, in the sense of bundle and Hammond are T-dual if this pullback of these two tree forms to the corresponding space is an exact form. For some F, it should be as a T to M invariant form, and don't degenerate on the fibers. Okay? This is a definition. And from this perspective, we have a relation between this kind of T-duality and the generalized complex structure. And we have this generalized complex structure introduced by Hitchin, and also developed after by Marco Volcherelli. And this is almost complex structure on this double bundle. And generalized complex structure as a complex symplectic boson structure as this particular case. And there is a nice remark theorem from Cavalcanti and Marco Volcherelli about this compatibility of the generalized complex structure in the T-duality. In the sense they can exchange symplectic and complex structure twisted by this H flux. Okay, this is just a small introduction because we are interested now in the spherical T-duality. Okay, this is almost the same, but now we switch this fiber. Instead of Taurus, we consider SU2, it's a S3, it's a sphere. Okay, This is introduced by Bogner, everything in MI. And the picture is almost the same, but now instead we start with Paulus bundle, we start with S3 bundle. Okay? 2 S3 bundle over the same base. Okay? And now instead we consider 3 forms, we consider 7 forms. Okay? Representing the secondary charge class, the push forward is this class. And we say that the pair is a set of T-dual if the fit is this diagonal. Okay? This is very similar to this T-dual.
But here is a SU2 bond.
SU2 bond, SU3 bond. So not please forward not.
But then the second general class, so it has to be SU2.
Yes.
Okay. So it's not that it's just more generic, it could be just any sphere bond. Because it's a different automorphism.
I see.
But
No.
I was asking, so this is an SU2 bond.
SU2 bond, yes. I understand. This is SU2 bond. It's not SN bond. It's SU2 bond. With the group structure is important. Okay, and this is a structural theorem about the existence of these pairs. Okay, and if you start with S3 bundle and the second chair class given by C2 and the H74, and there exists the dual pair in this case. There exists the H hat will be the corresponding on this H flux in the other side, and under additional condition, you have some unit pair. Okay, this is the basic setup. Okay, and this is if you look at this original papers from this Bogner, everything, Matai, they prove several results on topological level and the free theory level about this, how this behavior under duality. Okay? But it is not about some geometrical structure, how to do this. Okay. Now we start with the just recall as a very classical subject, but we try to fit a lot of things put all together. Okay. Now the first ingredient is the spherical duality, and the second ingredient is the called Müller manifold. Okay. We started now spherical one. Okay. Is a linear if the structural group is a orthogonal group, okay. Or some equivalent way the transition function takes values in the okay. And we have some bijection between this set of linear bundle over SK bundle over SL and the pi n of SOK. And we are looking in this case because we are interested in the S7, in the 7-dimensional sphere. And then for this case, this number will be important. The party of SO4 is a 2-interval. And a linear ST bundle over S4 is usually called a Müller. Okay? It's a S3 bundle over S4, linear. Okay? And just recall the Müller construction. This is the construction of the exotic sphere. Okay? We start with a pair of numbers representing class pi 3, and using these two numbers, we can build a map from S3 to SO4, and we can describe this very explicitly. And when this juxtaposition, this is just a multiplication pattern, okay, over S4, and we can define also diffeomorphisms from S3 cross S3 to S3 cross S3. These are in a very explicit way. And now we consider this manifold. We take the D4 cross S3 and D4 cross S3 to hops, and the boundary is S3 cross S3, and then we glue it, this on the ball. Okay? We glue it by these diffeomorphisms. Okay? For each Mn, you can produce a manifold. Gluing, this is a topology. Okay? And the remarkable theorem of Milnor, this is a homeomorphic to S7. This is always a homeomorphic to S7, but is just sorry. This is a homeomorphic to S7 if and only if M equals M is plus minus 1, and is not diffeomorphic when M is equal to 2. Okay? Okay, you can always produce, but we have a complete classification when this is a homeomorphic or not, provided by using type. And then here, just for reminding, we have some invariants introduced by Newman. One of them is a lambda invariant. Then the number of structures is different. You can put it in the construction. And if this lambda invariant is different from 0, we have a manifold that's not diffeomorphic to the 7-dimensional. Okay. And now with our first remark here, we can put the two pictures together. We can put the picture of this spherical dual and the Milnor construction. And in the following, if you consider this Milnor bundle, principal or not, here, principal I mean by ST bundle, principal ST bundle, because of this Milnor bundle are SO4 bundle, but they can reduce it to ST or not. But if we start with a Milnor bundle in a H flux, is a 7 form, D lies in the S87, then we can produce this T-duality diagram. Okay, this is our first remark. Okay, in this case, spherical duality and Milnor construction can fit put in the same pattern. Okay, and this is a very symmetric. If you look this K remains, but the M and the J is switched here. Okay, this is a very symmetric. This will have we can produce a lot of implication. This symmetry will produce a lot of consequences. I will show you in a second. Okay, and in particular, we can produce some duality between manifolds of homeomorphic to S7, but not diffeomorphic. We can show this manifestation of the exoticity in terms of the spherical T-dual. Okay, now I introduce the third ingredient, okay? Spherical T-dual, Milnor construction, and now we call the star diagram. Okay, okay. I just put some technical slides, but I just tell the philosophy here. I guess it's better. Okay, but this is just because we have some. I don't know, maybe an interpretation, description of some exotic spheres is provided by Gromov remark, okay, using loop action. And this allows to study some geometry in this exotic sphere. So it's this two Gromov remark proof that is, so this is exotic sphere emitting Riemannian map with no negative sectional curve. And they use this via by Riemannian dimension. I showed the construction. But this star diagram is just put this idea in some conceptual way. Okay? Just use some group reaction to study exotic manifolds. Okay? And this section is based on several people. Started with Gromo and Meyer, and Carlos Duran is a student of Gromo. Rigas is a past professor in Campinas. Laurent Esperança, a student of Duran, and Cavanaga, a student of Esperança. There are several generation people working on this. And I try to explain this picture, okay, but I will avoid the details, but the main philosophy here is start with some action dot in a bundle here, and you produce another action star that commutes with this dot action. And the idea is you can split your space in pieces using one action, and then gluing the space using another action. And in such a way that you preserve the space. You split the space and glue it again, and the space will topologically the same, but eventually the structure, the differential structure will be different. Okay, this is exactly what Blomer and Meyer did. Okay, I put a lot of, I guess this is a very explicit what is action operate, etc. I will skip this. Because I'd like to spend some time in okay. Okay. But this is okay, just this remark, okay, there's a lot of manifold are constructed patching subsets together, and we have some actions that provide this cocycle relation, and we have some explicit function gluing pieces, okay, and the action will produce some equivalent relation, and okay, this is already conceptual, but this is the fundamental, but I really skip this. But the main theorem is if we start with a principal bundle associated to a collection, this is a hypothesis. This is a special action that teaches how to split your space. Okay, this is a collection of functions, and in this case, this principal bundle admits a new action, such that this free action commutes with the original principal action, and the quotient by this new action is equivalent if you morph to this M prime, and the action on each subset is a cover of the manifold restricted to this G action, and we have this adjoint map to combine these two things. Okay. And under certain conditions, a principal bundle admits this collection. Okay, this is a hypothesis. I don't tell you how to produce this collection, but this is a theory. But let me show in an example, because this is the construction for Gromo and Meyer for an exotic 7 sphere. Okay, they start with this SP2. And they start with this principal bundle. This is a projection on their first column here. Okay. This is the standard S7.
So is something I don't understand. Is it S7 and H? So quaternions. So the unit sphere of quaternions is S3. So either you think of octonions or you think of S3, isn't that right?
Each column is belongs to S7, so it's like
Yeah, it's a unity.
Each column belongs to
Yeah, it's a unity in R8.
In R8. Okay.
And okay, each of them are quaternary. You can think in them, R plus H plus H. Okay. Any more questions? But this is this action here on the left here is a standard with quaternary multiplication. And then now, this is a action built by Meyer, another action. Okay? On the base, on the S7. And then when you take the quotient map by this action, you arrive in the new manifold. It's a sigma 7, GF. And then they prove this is a monomorphic class 7, but not diffeomorphic. Okay? By now, we have, for instance, you can do Riemann geometry here. You can make some Riemann explanation. And then this you can use in the new formula for curvature, etc. You can produce a lot of okay. But using the model is when you use the group action, you can put your hand in working. Okay, and the very interesting here is we can put the Mueller manifold in this diagram, star diagram. All this Mueller manifold can produce with the double action. Okay, this is the remark here. And this is a very explicit action. We can describe it all. And this is the first remark with the bundle. This is Mueller spheres. Can be realized as a S3, S3 bundle. This is a double bundle, like the generalization of this Gromov-Meyer construction. And now, our next remark is this diagram, double quotient, is the same as spherical T1. Now we have another interpretation. It's the same phenomenon in the several points of view. Okay? And if we start with a spherical T-dual pair over S4, then there exists a manifold that is a double action that fit in this diagram. Okay? And okay, in contrast, given a star diagram, there exist two forms H and H hatch, such that the stars are spherical T-duals. Okay, and then some examples. For instance, if I start with this M, 1 minus M, is a principal bundle, is a spherical T-dual to this pair. And if you start with M11, this is the diffeomorphic to the unit tangent space of S4. This is there exists some exotic structure here, is a very S7 manifold. But we are also how to understand this in this T-dual setup. And we can also put this Gromov-Meyer sphere in this context of this duality. And now we move for the second part. We start to homotop Hopf manifold. Okay. The Hopf manifold is a odd-dimensional sphere times S1. The complex, symplectic, etc. We are more interested in S7 times S1 in the 8th dimension. Okay? S7 times S1. And would you like to this just some remark? This homotopy Hopf manifold are studied in the 60s by the Blieskorn and Van der Vet, but here we are for different approaches, very different. And we started to put this Hopf manifold in our star diagram. And this is how we see. This is equivalent to the T-dual diagram also. Okay, and now our next remark is if you can put our manifold in a double action diagram, this is a star diagram, then M admits a G-invariant complex structure if and only if M blind also admits. But this is a structural result, and you can just do this by using the group action, because if you don't do this, is a little bit difficult. And for in our case, when we start with the 7-dimensional Müller manifold times S1, let's assume that there exists a S3 invariant complex structure and satisfies the L-bar lemma. Then any spherical T-dual also limits the S3 invariant complex structure. And we have this following non-Greenwich homology group. Okay, these are tricky computation. And we have also the Hodge numbers. And the main idea here is a T-duality permutes the Hodge numbers, producing some symmetries on the Hodge diamond. For instance, this is the Hodge diamond of the regular Hopf manifold, S7 times S1, and this is the exotic sphere times S1. So I guess this is for the normal magnetic sphere. And they are dual, they are spherical T-dual, and this reminds a little bit of symmetries, duality in symmetries in the Hodge diamond. Okay, and this can be covered by this T-duality. In particular, we can use this T-duality to determine when a complex structure on exotic manifold are non-equivalent. Okay? And this is a kind of old question proposed by Briscoe and Van Leeuwen, because Briscoe and Van Leeuwen showed that exists exotic Hopf manifold admits complex structure. But they put a lot as a question, what is this equivalent or not? And then we can make analysis by duality.
So when is the condition of this? When this assumption holds, are you assuming that there is an invariant?
You mean by
does it always exist?
For the sphere, yes. You mean the L-bar lemma, because this is from the strong Caehler torsion is admitted with L-bar lemma.
So you mean this assumption always holds?
No. Yeah, we assume it, but for Müller spheres, because this is a general Müller bond. Okay, because for this S7 times S1, there is a complex, but no Caehler, of course, but there is holds some relation complex.
So it holds for this 28 Müller 7 sphere, right?
20?
28.
Okay. Yes.
So for I remember it's you can see all the 28 of them, not only.
No, because there's two kinds of this. Because there is 16 are S3 bundles.
That's right. Mm-hmm.
And the other all are SO4 bundles, but you can reduce for 16.
16 of them.
Yes. But for here is you cannot use it.
Mm-hmm. Mm-hmm. And so only for this 16 you can prove the lemma, or?
Yeah, but it's a computation by hand. Okay. And now we go to to the third part of the topic. Okay? This is the generalized log transform, how to put this in another perspective. Now we are arriving how we can connect this with this part of the model. Okay? Because Ludmil ideas, the first was how can you generalize log transform, okay, for the high dimension. This is there's a lot of definition of the generalized log transform. For instance, Ernesto Luperci collaborators does different versions of this operation, but we need to understand what we relate. But this is the ongoing for the future. We will do this at some point, but probably there's some relation. And then just to remind you what I mean by log transform, I just remind this classical log transform. For me, is a operation to differential topology. Surgeon, okay. We start with an elliptic fibrillation, okay, and remove a fiber, put a fiber, and then glue it with this D2 plus D2, okay, and within a orientation reversing diffeomorphism, okay, and then we call this degree of this log transform is the degree of the. Okay, in this case, we start with the for a manifold X, the fibrillation, the fiber is a point, and we just make this surgery on the fiber. Okay. And we denote by xn p1 to k the manifold obtained by this k logarithm transform. You can do this on k fibers, okay, and with the degree j. Okay. And then we start from an elliptic fibrillation over S2. Okay. And Gomf introduced the concept of the nuclei of the elliptic fibrillation. Okay. It's a relevant part of the elliptic fibrillation. Okay. They show that it is all operation can realize inside this nuclei. We can just make this surgery to pick the fiber inside this nuclei, and then they describe how is the end this nuclei is the homotop type of this smash product of these two spheres, and the boundary of this nuclei is a Brinstorm homologic sphere, explicitly given by this equation. This is a work of Gomf. Okay, and we have the elliptic fibrillation and a relevant part of this nuclei. Okay, and this is associated with some singularities.
Can I just very briefly look at the formula for the log transform again, the previous one? So just very briefly, this you will of course not obtain multiple fibers.
Okay, we restrict it to simple fiber, to no multiple fiber. It's a minimal elliptic fibrillation. As the word is minimal.
So no multiple fibers, just smooth membranes.
Could you, I'm sorry, could you, so I mean, in this growth transformation, you can, why you don't obtain multiple fibers? Like,
no.
No.
I'm assuming by the beginning. Okay. I just restrict to this concept.
But again, it's because it is minimal, isn't it?
Yes.
Because this integer is just kind of one, you know, so...
Yeah, because I work in families. For each integer, you can have a family of these minimal elliptic fibrillation parameterized by some... This is the end. It's a parameterization of the minimal elliptic fibrillation. And that is a theorem of Gomf. If you have the nuclei of two elliptic fibrillations, if these nuclei are diffeomorphic, if these two nuclei are diffeomorphic, then we can extend the diffeomorphism to all states. In other words, this is really the relevant part of this operation. Okay? All happens inside this concept. Okay? And to understand the different diffeomorphism type comes from the local transformation, we need to understand the nucleus. And you can produce exotic form manifolds with this operation, like the exotic K3, exotic Logachev's surfaces. And just put in an example, if we start with the four-dimensional Hopf manifold, SP cross S1, we have this disk decomposition of this manifold, and again, we just can decompose the manifold in these two sets, and they do it by this diffeomorphism on the boundary, is three torus. Okay? And this is, in this case, this is just the Hopf map, on the Hopf map. Okay? And from this perspective, local transformation are, and another smooth manifold, X prime, obtained by these straightening angles of this depicted in the same set, but you need to change the diffeomorphism of U. Okay? For some choice of the orientation preserving diffeomorphism. Okay? In this case, you can just look at this like element of SL in Z, because you need to go to torus. Okay? And this is very important because we would like to imitate this for our setup. Okay. And now we are going to propose a definition of the log transform in our setup. And we proceed as we start with this decomposition for some odd dimensional sphere kind of S1. Then we start with this decomposition. And for a given diffeomorphism phi, and then we say this higher dimensional localization transform or generalized log transform, if I can make the stating angles, like the previous case, twisted by a diffeomorphism. Okay? This is similar to the, just imitate the previous case. Okay? And we just consider this special case as this homotop 7 sphere. For this example, we can just to remind how to build this. This is the Neumann construction. We just have this disk decomposition with this diffeomorphism F. And we have this S7 cross S1 with this disk decomposition. And on this S1 factor, we consider the identity. And we can produce another manifold by the diffeomorphism phi, such that we can go for one diffeom to another by an appropriate phi. Okay? And then we can show this explicitly. Okay? But look, this will provide one Müller series, and you will provide another Müller series. Okay? And okay, just in the but if you recall, this operator of the gluing is equivalent to this spherical T1. Okay, and then we are really going to the surgery along the fiber. Okay, in the H dimensional, with the base is 4 dimensional, and the fiber is another 4 dimensional. We'll just make the search at the differential topology level. And if we consider this X, the manifolds that are homotopically equivalent to S7 cross S1, mod out by difference, up to diffeomorphism, and we can show that this group, this is a finitely generated abelian group, and the operation is log transform. We can switch for one homotopic Hopf to another by doing this operation. And now we can put it all together in a same picture. Okay? Now we can join the spherical duality and the logarithmic transformation for this Müller manifold. And here we have the spherical duality for this Müller bundle. And here we have this generalized log transform from one space to another. Okay, but it's several concepts are disjoint, but we can connect it all of them. By now, we'd like to go further and analyze if you have some analog to the nuclear, because we have some surgery similar to 4-dimensional, and we would like to understand if you have some concept similar to the nuclei, or in other words, this relevant part of this logarithmic transformation. And we can find some intensity lossy, and this will be connected with this talk in the morning. Okay? This part will connect with the part of the morning because of this relevant part will be appeared now. And if you start with this polynomial, this equation, this is based on work of Briscoe, okay? Because Briscoe can describe this exotic spheres using singularity. And for each of these K, we have 7-dimensional homotopic sphere. This is the work of Briscoe. And if you set this L to be 6 times 6K less 1, and Wi is this number, L over AY, when AY runs on this set. And then we define a C-star action on the 0 level set of this function. And the action, this lambda acts, the C-star acts with the weights, W0, W1, etc. And this is a weighted homogeneous polynomial of the degree L. And we can consider the fiber over the 0 intersect with the boundary of this ball. And then we have this manifold W7, 6K, and 1,3 is this intersection. And this is the work of Briscoe. And this is the homotopic 7-dimensional sphere. Okay. And if K is different from K prime, these are not diffeomorphic. These are homomorphic, but not different. And in particular, we can consider this C-star action on the fiber over the 0, which is 6 to axial action on this 7-dimensional space. And the close change was the structure of an orbifold. This is based on the work of Boyer, Galicki, and Kohler. And we have now another remark to this. Okay, this space, like, when you consider this space over mod out by this action, S1, we arrive in a 6-dimensional space. Okay, and we remark this is a fun orbifold. Now this start. Actually, this is the start of this story, because we start with the proposal of log transform, and we arrive in a relevant part. This is algebraic. Okay, and a at the beginning, the question proposed by Ludmil was what the relation between the differential structure and the algebraic geometry. When the differential structure proposed by Müller interfered on the algebraic geometry of this manifold. Okay? And this is the question. How the invariants of deformities of the homotopy sphere interfere in the algebraic geometry of V. Okay? And now, this is upon the end of the last year. And during 2024, we had a lot of fun because this connects with this blow-up form from chain 1. Because by now, probably you will show this tomorrow, this guy are not birational if the k is a different k prime. And then we can arrive this by using this new technique. Okay, we first solved this in another way, but now we know this is connected with this technology produced very recently by working with Leo in Kontsevich and Ludmil. Okay, and then now I'll finish the talk with this question. But this is just to motivate you the next lecture by Leonardo tomorrow, because tomorrow Leo starts from him. They explore this algebraic geometry of this analogous to nuclei. Okay? Because in fact this is a very relevant part. This suggests our proposal to Log transform is honest, because we can recover this relevant part of the operation. Okay? And I stop here.
Questions? No, it's all right. I forgot. Any questions? Yeah, there.
So you feel like it is like the Fourier Mukai transform? Something like that?
Ah, okay.
It is exactly Fourier.
Yeah. Is it another interpretation?
Any other questions? We will have the continuation with Leonardo tomorrow, so thank you very much. And then we will start in 10 minutes with Victor.
Yeah.
Sorry. Kenza, could you come 1 second?
Yeah, sure. And then I think it's
well, it's a great pleasure to introduce Professor Viktor Katzarkov from the Steklov Institute. And but your title, he will be speaking about.
Well, I don't remember the title, but something about fibers of Landau models in dimension 3, and maybe some questions about categories related to this.
Very good.
Thank you. So, first, thank you very much for inviting me here. So that's my second time in this place. The first one was something years ago, and just after I came back from Sofia, all borders were closed because of coronavirus in a week. So we will see what will happen next week. Okay, and, so I would like to talk about parts of this top meeting I was presented last time, but in general, so I would like to make a sort of overview, and then at the very end some new to discuss some new easy enough calculations. And there about so the general problem is I'm going to discuss is that if we have a smooth Fano variety, then mirror symmetry predicts that there should be a Landau-Milzuk model should correspond to a Fano variety. And in the first half of the talk, I'll briefly remind in what sense do I understand this Landau-Milzuk model, and how can they, in some cases, they can be constructed. And then I'll discuss their properties which correspond to homological or birational properties of the initial Fano variety. So let me just fix here a general picture of homological mirror symmetry, which I think is known in the audience. So if we have a Fano variety E, smooth Fano variety, so anticanonical class is ample by definition, then there should exist another variety called Landau-Milzuk models. So variety with superpotential I will denote by W. So convex valued function such that so according to homological mirror symmetry, this means that they have algebraic and symplectic categories, the right categories of where shift on X and a Fukaya category of X. So I'm not writing, so Fukaya category is a category whose objects are Lagrangians for some symplectic form. I'm not writing symplectic form here because of course it depends on the symplectic form. As well as this derived category can depend on complex structure. And this means that either I fix just anticanonical symplectic form line in the anticanonical class, or in the main example I will discuss, so for Picard and Fano triple case, all of them are all symplectic forms are proportional, so it doesn't we don't need to fix it. But maybe I'll discuss something depending on the variation of symplectic form. And for Landau-Milzuk model, there are relative versions of these categories. So the right category of singularities of y, w. So it's a product of categories of complexes of covariant sheaths, modular perfect complexes of smooth fibers. These categories are equivalent, so it depends on the fibers, on the single fibers. And here, for Kaehler category of Y, W, so whose objects are vanishing Lagrangians. And according to homological mirror symmetry, this for each x, it should exist y such this equivalent categories are cross equivalent. And in general, I will use, I think, so let us have this arrow equivalence number 1 and this number 2. So I will use the first equivalence to construct Landau-Ginzburg models. And at the end, I'll discuss something related to the second arrow. Maybe I will give very precise definitions for simplicity, just not to avoid details. Okay, so let's discuss first this equivalence between symplectic side of Pantev and algebraic side on Landau-Ginzburg model. And in this case, so as it was discussed on the second talk today, we correspond, so we consider quantum cohomology of X, small quantum cohomology, which can consider as a homology of Foucault category, but anyway, so it's a deformation of cohomology whose structure constants are prime three-pointed ground-Witten invariants. Counting rational curves, dynamics, and having this, we can construct. Well, we can construct the Brownian's connection or quantum differential operator. So, I'll just. So I'm not going to discuss this, but if you have a torus neuron severe torus, so the torus coordinates on which is correspond to divisors, and a trivial vector bundle whose fiber is cohomology or even cohomology or algebraic cohomology. So there are different versions of this, and there you can get quantum multiplication by canonical class. So the one that was considered for the construction of atoms. Then it defines a connection. Well, maybe you need make some so-called regularization, but anyway. So this quantum differential operator is just certain differential operator whose coefficients depends on ground-Witten invariance, and it has an analytical solution which is a generating series for one pointer ground-Witten invariance with descendants. So to be slightly more precise, solution we denote it I0x of t, which is the sum of ground-Witten invariance with descendants. So for those who are familiar with this, so here we have fundamental class and dual on it. So t to beta, so sum over beta. So some certain we can erase this. We can consider it as a certain formal series which can be constructed through, from Pantev, and in the cases we are going to discuss, it is known, it is computed mostly by Guittar's theorem, who described how to do this for, say, completely sections in total varieties, or some other people who took this for Prismanians and so on. So this is some known data. So if you are not familiar with this, it doesn't matter. And on the other hand, if we have let's imagine that we have a function, we will call it f from C star to n to C. So usually n will be the dimension of x and also the dimension of y. So one dimensional model can have a dimension which differs from the dimension of the Van variety, but for us we will deal with varieties of the same dimension. So, so this C star to n can be considered as an open chart on y, and why it is useful because it is easy to describe some combinatorics, since the map from C star to n to C is nothing but just a Laurent polynomial. And we will use it to construct y in the following sense. So now I'll give you just some simple example, and then I give a definition of. So this is a prototype for this Laurent polynomial for Landau-Weisel model. So let if x is just P2, then one can compute that I0 of P2 of T is the sum of 3k factorial over k factorial cubed to T to 3k. Just this simple formula. From the other hand, if we choose f is x plus y plus 1 over xy, so well known. So when people write some one-dimensional model, so this is the simplest, the first example. Then we can let us compute. So we can usually. So we'll speak about Landau-Weisel model either as a Laurent polynomial or a family of fibers of given weight. So we can consider the family f equals to lambda, where lambda is a complex number. So we have a family, and we can construct periods of this family. So we choose a fiberwise form, a fiberwise cycle, integrate over it, and get some function. So the theorem says that in this case it's very easy to compute a period, analytic period of this family. So we denote that I y is of T. Let us define the following series. It's the sum of f to k, and so let's break it like this: f to k, 0, t to k, where so f to k is 0 is just a constant term. So if we have a Laurent polynomial, we consider its power, so it's some another Laurent polynomial, we can take its constant term. So fk0 is constant term of f to k. And theorem says that such a series, which can be easily constructed from Laurent polynomial, is a period of this family f equals to lambda. Just in our example, it's an easy exercise that if we consider x plus y, x plus y plus 1 over xy of t is exactly the sum of 3k factorial over k factorial cubed t to 3k. Yeah, only so non-zero constant term can appear when we multiply, say, 3 polynomials and to cancel numerators and denominators. And so this correspondence between periods and the solution of quantum differential operator is what is called mirror symmetry operations of Hodge structures. So I'll skip explaining this name, but it is a base of the version of mirror symmetry I would like to discuss. So let me make a definition. What is Landau-Weisel model? So if we have fun overriding x, then a Laurent polynomial in n variables where n is the dimension of x is called toric Landau-Weisel model if the following 3 conditions hold. So the first, so let me maybe change the order. So, but anyway, the first and basic one, why should ix 0 of t should be equal to if of t. So these 2 series should coincide like here. Then toric condition, which we will not discuss, or maybe slightly discuss at the very end. So toric condition claims that there should exist a degeneration of x to some toric variety t. Usually it's almost always is singular. But it doesn't matter for us, such that the Newton polytope of this Laurent polynomial, so convex hollow of all its non-zero coefficients, should be equal to Fan polytope of t. So if we have a toric variety, we can draw its Fan, then take generators of its race, integral generators of its race, and take a convex hull of this integral generator. So maybe so the third condition will be more interesting for us because we'll discuss it. So, say for this example, we can P2 is itself toric, so we don't need to consider degeneration. Then the Fan of P2 is it's known can be drawn like this. So we have this triangle, and this is exactly a triangle Newton polytope for x plus y plus 1 over xy. Yeah. So here is x, here is y, here is x2 minus 1 minus 1 over xy over xy. And the third condition is this is mirror symmetry operations of Hodge structures. This is sort of imitation of 2 facts. First of all, Grom-Witten invariants, Grom-Witten theory, the symplectic invariants, so they don't change under deformations. Of course, here it's not literally like this because this is true if the toric variety is smooth. But so it also was discussed possibly today that there are still some deep relations between Grom-Witten theory of T, or perpendicular resolution of T, and this and the initial Fan variety. And the other thing is that is a mirror symmetry for toric varieties. So roughly speaking, a mirror dual toric variety is just dual toric variety defined by dual polytope. So combining this as a motivation, you can pose this condition. And the third one is related with, so we started from some motivations from homological mirror symmetry, some categories which are related to singularities of singular fibers. But then when we write just a Laurent polynomial, this means that we write an open chart of a Landau-Ginzburg model. And of course some singularities can be not in this chart, and then we lose information. So to declare that for a wise compactification of this the historical Landau-Ginzburg model should be good for homological mirror symmetry, we have this our third condition, which is called log or not log Calabi-Yau compactification, claiming the following. So if we have, let us have this C star to n. This is our polynomial C. So the following picture should exist. So we should be able to embed our C star to n to some smooth, non-compact probe over C variety, which is a Landau-Ginzburg model, such that all fibers are all fibers are Calabi-Yau varieties. Of course, they can be singular or even reducible. So anticanonical class of Y is trivial and Y is smooth itself. So yeah, and the fibers should be compact. So this means that just fiber-wise compactification. And this is our Landau-Ginzburg model. But also it's it turns out that it's useful to add to compactify it completely, so to add fiber over infinity. So this is called U, and this this picture is just a Calabi-Yau compactification, and if you compactify over infinity, then it's called log Calabi-Yau compactification. And the condition is Z is smooth over C. So there are some examples when you can have unavoidable singularities over infinity. And the canonical class of Z is just a fiber. And later we'll discuss what do we add here, so this fiber over infinity, its property, and so on. Okay. Of course, if anticanonical class is a fiber, then when you delete the fiber over infinity, then the anticanonical class of Y will become Calabi-Yau variety. Okay, so that's a definition, but let me briefly mention how this compactification can be constructed for given Laurent polynomial. And this procedure called log Calabi-Yau compactification procedure, it's not always not automatically works. So it works for some good cases, but fortunately a lot of cases are good. And its another advantage is that it has several interesting, useful consequences we will discuss. So let's log Calabi-Yau compactification procedure. So the general idea is that if we have some family of hypersurfaces in a torus, so Laurent polynomial is equals to lambda. And we have, so let delta be a Newton polytope of F, so the one that corresponds to this toric degeneration. Then we can consider the dual polytope, so like in mirror symmetry for toric varieties. And inside this dual polytope, this family of F equals to lambda will be an anticanonical family. So it's a family of compact projective varieties whose anticanonical class is automatically 0. So which is actually the most complicated thing here. So let me give more details. So consider the polytope nabla, which is dual to delta. Then you can consider toric variety associated with nabla, and there the family f equals to lambda, or its compactification. So where here we can consider lambda as a point on P1, not just a number. And then this is a canonical linear system. So one-dimensional linear system in a complete and canonical linear system. But of course, that's not enough for us, just because of two things. First, this. First, assume that nabla is integral. So to make statements like this. So this can be generalized for non-integral, for in some cases for non-integral polytopes, but anyway. So this means that this toric generation is Gorenstein. Then we can compactify this family in T nabla, but we have two problems. So first of all, T nabla also can be singular, and second, this family has a base locus, so it's not like this. But in good cases, these problems can be solved. So another assumption, we can consider Crepant resolution T nabla delta to T nabla. I assume that there exists a Crepant resolution. So combinatorially it can be constructed easily. You just have this nabla is a polytope with a unique strictly internal integral points, so the origin. So all its integral points lie on a boundary of nabla. And you add raise to all these points and subdivide, triangulate your polytope, and you get a Crepantly equivalent toric variety to our T nabla. And in good cases, this variety is smooth.
But if it's not a polygon in the plane, how do you triangulate it?
Well, it's not triangulate, divide by simplices. You just yeah, so you consider toric variety with this rays. Of course, that's not a unique procedure. You can make some flows and so on, but I assume that there exists. Maybe in 1 minute I will give an example. And also assume that, then you have a smooth, the situation is much better. You have a smooth toric variety and canonical linear system. How does it look like? So it's generated by some general fiber, and the fiber over infinity, so corresponding just to constant, which is nothing but the boundary divisor of our toric variety. So this boundary divisor consists of some number of components, and the base locus is the intersection of general element with each of these components. It's easy to see that this intersection, so it's some dimension 1 subvarieties for each component, maybe reducible, but this base locus is never torus invariant, so no dimension 2 toric strata lie in the base locus. So then you just blow up these various components one by one. After some blow-ups, maybe new ones can appear. But let us assume that it's they are general enough. So this can be said more formal, like they intersect torus invariant, dimension 2 torus invariant subvarieties transversally. So assume that blowing up base components one by one, we resolve base locus. So in general, in principle, when you blow it up, you can get the singularities, but let us assume that they are good enough not to get the singularities. Just for our example, if we have P2, then the dual toric variety is just a toric cubic. So here is it. It has 3 rays, but it's singular here. Then Krapin resolution is just adding rays to these integral points. And then you see that this factor over infinity will be a wheel of 9 rational curves. So as it is expected for Landau-Ginzburg model for P2. Yeah, and so then blowing up base locus. So when you blow up the base locus, you never, since this fact that there are no codimension to torus invariant components, this means that all exceptional devices, they either become horizontal or they go to fibers, and one can keep track on this, and so that's how we with Ivan Shiltsov checked for Finite triples Katzarkov, Kontsevich, Pantev conjectures. We just carefully computed where these exceptional devices go to. But I'm not going to talk about this. I just want to discuss some properties or some good things which I need, which can be extracted from this procedure. Invariance of X from F. So the first one, so it's like historically the first among these observations I'm going to talk about. It was historically the first one. Let's so all of this invariance, so all this phenomena will be related with fibers, and usually our main example will be Fana triple. So Fana triple with the current one. So we have 4 types of fibers. So first one is just smooth fiber. Then fiber can be singular but irreducible, just with isolated singularities. Or it can have some number of components, and it can have component. So there is a special fiber which is a fiber over infinity. So we'll talk about all of these fibers. So the first one, let's discuss some reducible fibers. Let's define Kf, the number of reducible components of reducible fibers minus the number of reducible fibers. So if you have a reducible fiber, so if you have 2 reducible fibers, one with 3 components and one with 2 components, then you should compute 3 minus 1 plus 2 minus 1, which will be 3. So this number will be 3. Then conjecture says that Kf is equal to h1 n minus 1 of x. So when I computed it, it was a big surprise for me, because of, in all this picture, compactification, quantum cohomology, Laurent polynomials, and so on, we used only even part of quantum cohomology. We didn't use the odd part, but for one of triples. But it turns out that at the very end, somehow we can compute the dimension of intermediate decoder.
So this is in dimension 3?
No, conjecture in no dimensions.
But checked in dimension 3?
Yeah, so that's what I wanted to say, that the theorem of me with Chilsov, and me with Shramov says that conjecture holds. So for the surfaces, it's for the dimensions 2 and 3. So for 1 and 3% for the surface, and for complete intersections. So it's just some mixture of, for complete intersections, it's a mixture of complicated for me, but not for combinatorics. So some complete combinatorics plus classical algebraic geometry, blobs, and so on. So for complete intersections, that's also true. And maybe some, so there are some other examples.
So I mean, this might have nothing to do with mirror symmetry, just how the homology are computed combinatorially for complete intersection.
No, this number is for under model.
But it could be translated some combinatorics, therefore you don't need to connect it with mirror symmetry at all.
Yeah, but there's a statement about some Laurent polynomial. Yeah, but so this, I mean, so there are some. I mean, when we say that something holds for something, this should be formulated carefully. So for complete sections, this means that for Laurent polynomials going back to Givental's Landau-Knuth models, this is true, because I don't know. So I don't have statement like when something can be proved for all Landau-Knuth models, with some exception in dimension, say, 3, because for Picard, because of what I'll talk in several minutes. And also maybe let me formulate a theorem which holds. So it's not a theorem; it's check of comparing two existing coincidences of two existing lists, which is indeed only for Picard one of triples, only in dimension 3. There may be.
So also, I mean, when you define it like that with number of fibers, so is this for generic Landau-Knuth model or for the canonical Landau-Knuth?
Yeah. So I'm always talking about Landau-Knuth models for canonical class.
Okay.
Say like for delta surfaces, for general divisor, you don't have reducible fibers at all. But for anticanonical, so anticanonical Landau-Knuth models is very degenerate, so it usually has a lot of components. So for X Picard one threefold, so this reducible fibers fiber is unique. So either all fibers are irreducible, or only one fiber is irreducible. And so we counted numbers of components here without multiplicities. And theorem says that's what we checked with Ludmil. But we just compared two lists of Niskovsky and some other people who computed rationality question about one threefolds and Gauss's computation of monodromy. X is rational. Theorem says that X is rational if and only if there are no multiplicities in irreducible fiber.
So
all components are of multiplicity 1.
I mean, this is actually a statement which is very much similar to research in particles, elementary particles, and so on, because I mean, in elementary particles, more money you put in the investigation, more elementary particles appear. So here, I mean, I'm old enough to remember that the list of funnels with PKRZ has changed quite a bit in the last 30 years. So, I mean, who knows? I mean, if you put more money in this project, maybe more three-dimensional PKRZ funnels are going to appear.
No,
so you need to specify for known.
Well, everything is for known. So. But I mean, the list of PKRZ funnel threefolds didn't change for 50, so
for what?
Post classification, because
for what? Didn't change for what?
From I mean, so when it's classified this 17 families, indeed one particular variety with one family, Mukai Memura 1, was found. But when I'm talking about this, I'm talking about families of fun varieties. So everything.
But weren't there two more families added by Mori and Mukai?
So one family was added in 2200.
In 2002.
Yeah, but it's in Picard rank 4. But there are another evidences that the list of families is complete.
So what is the equivalence? What is it equivalent to? No multiplicity in the reducible?
No, so you have a this unique irreducible fiber. If you want, if you would like, I can say that its monogamy at this fiber is quasi-unipotent always when you go around it. And it is unipotent if and only if the fun variety is rational. Which is also quite surprising because I mean, how rationality can be involved in the picture. So I don't have an explanation. But there are another more strong generalizations of this first conjecture about one Hodge number, like Katzarkov, Kontsevich, Pantev conjectures, or equal to double conjecture, which involves mixed Hodge structures in the picture. But I'm not going to talk about this now. Let me just so we discussed this reducible fibers. Then what's the order? Okay. Then smooth fibers. So for smooth fibers, I just so that it's not a conjecture. It's like a fact that for finite triangles. So mirror symmetry for fun varieties can be considered as a mirror symmetry for anticanonical Calabi-Yau varieties, which should be mirrored to fibers of Landau-Ginzburg models. So for three-dimensional case, anticanonical so Calabi-Yau surfaces, they are K3 surfaces, which have very nice properties, like Taylor theorem, and they have lattice. Its middle cohomology has a lattice in it. And for mirror duality for Calabi-Yau for K3 surfaces, a version of it was described by Dolgachov and Nikolin, and roughly speaking, they said that if you have a family of lattice polarized K3 surfaces, then you can consider so this lattice is a lattice of algebraic cycles. Then you can consider another family when algebraic and transcendental lattices interchanges, and can consider a family whose algebraic cycles are transcendental cycles for your initial family. And this duality is called Dolgachov-Nikolin duality, and we proved with a lot of people, so it's Doran, Katzarkov, so Harder, alphabetically Harder, Andrew Harder, Doran, Katzarkov, me, and Ovcharenko. So theorem says that for smooth Fana trifles, anticanonical divisors are Dolgachov-Nikulin duals for two fibers of compactified Van book model. In the triple case, there is a sort of approach how to define in a unique way Van model, but so it's maximally rigid, maximally mutable, back to maximally rigid, maximally mutable around polynomials. But let's skip the details. Now I'm going to discuss fiber over infinity. And I would like to finish with fibers with isolated singularities, and maybe, so I have some questions on them, maybe somebody can suggest an answer. So let's make a motivation. So if you have imagine that we have a good Fana variety and a good Van model. This means that Fana variety for which we have a toric Van model, and this log Calabi-Yau compactification procedure described here works. So all these assumptions are satisfied. So for most of Fana, so this is true, say, for most of Fana triples or for completed sections as well. Then if you have your Fana variety, so we have by definition of toric Van model, there is a degeneration of x to t, and then it's easy to check that the dimension of anticanonical class of x is equal to the dimension of anticanonical class of t. So that's because toric variety can be single, but singularities of these singularities are Borenstein. So that's easy to check. And then, but if we have now we have a toric variety t, how can we compute the dimension of a canonical linear system of a toric variety? We should consider its fan polytope, consider this dual polytope, so in our terms this nabla, and count the number of integral points inside this polytope. Well, and subtract one because of projectization. But the number of boundary of integral points inside nabla -1 is exactly then, since it is Gorenstein, it's exactly the number of integral points on the boundary of this polytope. And this number is exactly the number of anticanonical torus invariant divisors, so toric boundary for T nabla delta for its resolution, because that's how we constructed it. And since when we blow up, we don't get an exception divisor going back to the fiber over infinity, then this means that this is this number is equal to the number of components of the fiber over infinity. So u-1 of infinity. In some cases, this can be checked even when this local area computation procedure doesn't work, but some generalization works. So let us pose the conjecture. So saying that the dimension of anti-canonical linear system of Fano variety X is equal to the number of components of one magnitude model over infinity. So this theorem was so the good thing, and as for me it's rare for studying magnitude models for Fano threefold case. It can be proved so in the way like this, and constructing local area computation not by case considerations, but in general. So I mean, for all of them simultaneously. So let me just fix theorem. So I don't make numbers of conjectures. So maybe one. So this is two. So we check this with Shiltsov. Again, conjecture 2 holds for Fano threefolds and complete intersections. And also, as I told, in some other cases, when you have a singularity in the fiber over infinity, of which you can't, which cannot be avoided. In some cases, this conjecture also holds. And let me just note that if we believe, of course, this conjecture after conjecture, so because it's, I mean, a lot of things in mirror symmetry. So if we believe this conjecture, then some strong classical algebraic geometry conjecture holds, like Kawamata conjecture that anti-canonical linear system of smooth Fano variety is not empty. And different people proved this conjecture in dimension up to 5, if I remember, maybe up to 6. I don't remember, maybe up to dimension 5 or 6. There are different strong mathematicians check this. And this conjecture implies that the anti-canonical linear system is 6 dimension, it's not only 0, but at least 1, because we anyway have a fiber over infinity. So this number should be at least 1. And also there are some, it's related to some problems of Caehler and Xu, who told that, so it can be formulated in a more strong way that the dual intersection complex of fiber over infinity should be homotopically, it should be a sphere of maximal dimension. It's like in degeneration of K3 surfaces, so Kulikov classified them as semi-stable degenerations, and when the monodromy is maximally unipotent, as we have here, because of mirror symmetry, because it corresponds to Lesher separator of multiplication by anti-canonical class. Then this degenerate K3 surface is a union of some rational surfaces forming a two-dimensional sphere. So this can be conjectured in all cases, and when the monodromy is maximally unipotent, Caehler and Xu posed a problem that so in the degeneration of Calabi-Yau varieties with maximally unipotent monodromy, it's also a triangulation of a sphere. So in this particular case, this should hold as well. Okay, so I have, fortunately, I have, surprisingly for me, some time, and I would like to discuss singular fibers of Landau-Ginzburg models which are irreducible. So let me recall that Fukaya category Foucault category is a category of whose objects are vanishing cycles to singular fibers, and it is hard to define it. But there is a special case when everything is okay with it. That is when we have a Landau-Music model is a Lefschetz fibration. So all single fibers have a unique isolated singularity. Have a unique isolated singularity. In this case, so if Y W to C is Lefschetz, then Foucault category has a full exceptional collection of objects corresponding to vanishing cycles to these nodes, to these isolated singularities, L1, Lk. Expectation. I've asked some symplectic geometers, but they told that it's they don't know even for examples how to prove this, or maybe at the moment they don't know. Expectation is that so let us imagine our case. So we have like for Picard one finite triple, we have a family of K resources with one complicated central fiber which is reducible and so on, and several fibers with nodes. In this case, the expectation says that in this case the Foucault category has a semi-orthogonal decomposition with an exceptional collection corresponding to these nodes and some residual category. So it's a sort of in mirror sense, so mirror kind of Kuznetsov component. So in general, Foucault of YW is just generated by some category and objects, some number of objects. I would like to discuss a bit this thing, but so it's natural. So let me just present a small table. And then pose some questions related to this. So I computed this singularities of fibers for all 17 Picard one finite triples, and let me make a table 1, 2, 3. So here I just put phonovarieties. It's convenient for me to count them. To indicate them by indexes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is index 1. Then 5 index 2 varieties 1, 2, 3, 4, 5. Index is 2. And then it's a unique variety with index 3, that is quadric. And the unique variety of index 3, index 4 is just P3. So here I'll write the maximal length of maximal known length of okay. So maybe to be like in my notes. Here I write the number of isolated singularities, which turned out to be just nodes. So here we have 1, 1, 1, 1, then up to 10, in 10 is 4, and here 2, 2, 2, 2, 2. Here we have 5, 4, 2, 2, 2, 2, 4, and 4. So that's just a number. And let me here present the known maximum length of exceptional collection. So let me start from simple things from the bottom. So here we have the same as in this line from 5 is also, but also there are some things, so something different in the first 4 cases. So here we have, in this case, we have greater or equal than 1, which means that, of course, any final variety has an exceptional object, which is a structure shift, but in the residue category, it's not known if there is an exceptional object or not. And
you skip 2.
Huh?
You skip 2.
Yeah, I skipped 2. That's true. I'm just talking now about this one, and here it's even more interesting thing. And my expectation, like for quartic, mirror symmetry predicts, so it's Landau-Diamond model, so Levin polynomial is very symmetric. There is an action of S4, so you can, so it's symmetric in four variables, which means that if the thing, so if it corresponds to, so if topological mirror symmetry holds, then it should be a lot of exceptional objects in this residue category, which I think for specialists not complicated to prove that there can't be too much too much then. And here I write 1 or 2. So this variety is intersection of quadric and the cubic, and there are 2 cases. This quadric can be singular or not, and of course intersection of quadric and cubic should be smooth. So cubic shouldn't pass through the singularity. And if it is smooth, then it has 2 exceptional objects. And if the quadric is singular, then it has 1 exceptional object. So what does it mean? I have a conjectural explanation of this fact, but it's in the field of symplectic geometry, which is I am not very good in. So what does it mean? Yes, say it like this, and also one more example. So I think the picture is like this. So you have some reducible central fiber, and this singular fiber, and vanishing cycles to this singular fiber is indeed an exceptional object, as it should be. And so it's like index k finite variety also always have k exceptional objects corresponding to O of 1, O of 2, and so up to O of k minus 1. And and there are vanishing cycles to something inside here. What means we took certain specific final variety, which this means that we choose some specific complex structure. In terms of Landau-Diamond model, this means that we choose a certain symplectic form. So in all these computations, we didn't use a symplectic form, but in some symplectic form, some objects can glued, like it happened in the derived category of intersection of quadrics and cubics, and start to represent the same object. And anyway, so this, so we see, and it follows from the last example I want to present, that actually these exceptional objects, they are not of this simple form, like vanishing to some node, vanishing cycles to some node. So they are not represented by some cycles, they are just some linear combination of them. So the last example is very simple. If we have considered P3 blown up in a line and conic, such that the line intersects conic like this. So plane conic, so it's not Fana, but I think such phenomena appears for, so it is not complicated to find such phenomena for Fana varieties, and anyway it's very close to Fana. So blow up a conic on the line, then of course it has so X has a full exceptional collection. just because P3 has a full exceptional collection, then you blow up two rational, so a rational, smooth rational curve and another rational curve. So, from the other hand, Kuznetsov's result, so example, so this example was shown me by Kuznetsov. There are, I don't remember, but there are exceptional collection on X. I forgot what's the number of elements, so I don't. L1, LK, so where K is less than how many? 4, 5, 6, 7, 8, yeah. So this full exceptional collection of 8 objects. Such that the residual category, we'll call it F, doesn't have an exceptional collection. So this means that the length of exceptional collection do depend on where you start from. So in the first case you choose an exceptional object, then one by one, and get 8 objects. And here you have less than 8 objects. So if this means that for me in mirrors, on a mirror side, these vanishing cycles corresponding to these objects are more complicated. It's not like if you have just several nodes and all exceptional objects are vanishing thimbles to these nodes. Just because this geometrically this doesn't depend, so you always can make a path to the node. So that's very interesting for me to study symplectic geometry. So category, subcategory in the Foucault category corresponding to this fiber with non-isolate singularities. But I mean, beyond my hope on symplectic geometries, I cannot do it by myself. So there are several questions related to this computation. Thank you very much.
Questions?
So it seems that this V5 and V22, you have also discrepancy between this 4 and 2 and 4 and 2, right?
What? Here?
Yeah.
So sorry. It was my mistake. Here should be 4. Yeah, so everything coincides here, except for the curve. So in rational geometry, lower degree Fano varieties have more rich and more complicated geometry in general. So it's not surprising that something happened on the lower degree.
So even 322?
Sorry?
322?
2? Yeah.
Thanks.
Two mistakes.
Okay.
Is that all? Yeah. Yeah, thank you.
Any other questions? Victor, thank you very much. And this continues in 20 minutes. 5.
Hi.
Hi.
All right, so we're very happy to have Zoran Davo, who is going to tell us about modular algorithms.
Thank you. Thank you very much. So finally, I decided to change my title. I would like to discuss or talk about something that we discussed about with Maxim Kontsevich last year. And well, there are many kind of versions of atoms we have seen already, and actually, so as a matter of fact, so this is maybe one version of atoms, so how to say, so I'm working with irregular simple connections on curves, and I will essentially talk about such objects. So this is maybe, yeah, so connection theorists' version of atoms. And so as we have seen, as we have heard in several talks, so first of all I will give some introduction. So what we can do is when we have a smooth projective variety, maybe some of these adjectives are not even needed, but one can come up with so-called Dubrovin connection using essentially well, quantum product. So this quantum product is parameterized by some parameters, and then one can actually consider an Euler field, which is just C1 of T of X, and then we can consider multiplication by this operator. So maybe let me put a star here. So this operates on kind of cohomology, and then this can be used actually to define Dubrovin connection or quantum connection. Okay, and I'm not going to write the formula for it. I mean, it definitely has C1 of Tx quantum product in it. The base is essentially, well, at least some formal version of the cohomology space of variety X, and then the fibers are also kind of the same space to some extent. So this is deeply related to homogeneous manifolds, and maybe sometimes one needs to restrict to some subspace of the cohomology, for instance, generated by algebraic varieties or some versions like that. Okay, and then for the purpose of this talk, we'll just focus on Dubrovin's connection. So, what are its properties? So the properties are that it has, so first of all, it's not known in general whether it is a convergent one, but let us assume that it converges. In many cases, actually, it converges. For instance, for surfaces or spherical radius. Actually, no counter examples are known. So assume that it's given by convergent formal series. Then, what are the properties? So the properties, first of all, it has one singularity of irregular type. So if maybe I don't actually assume that everyone knows what an irregular singular connection is, but I will explain this later on. But and I should actually put something like nabla x, because I already know this by nabla x, and then nabla x has irregular singularity. And it is even known that it has of Poincaré rank at most 1. Okay, and then what else do we know about it? Well, I guess that it's defined just over formal fields in general. So it's defined over some formal ring in general. Okay, and let me just focus on the first of these two. So Poincaré rank. What does it mean, Poincaré rank? Essentially, it means that it has a O order at most 2 in suitable trivialization. Okay, so then there is the theorem by Turitin, which states that it's possible to take some root, so adjoin some. I haven't yet introduced any variables, but. So up to taking some ramified cover, it is and up to tensoring with ring of formal variables, it is possible to diagonalize this. Okay, so but the point is that here we would like to consider the case when no such root is necessary. Okay, so this is actually. The notion of exponential type from commutative host structures, and this was introduced by Ludmil and Maxim and Tony Pantev. That actually, we assume that actually, so this is an assumption. That it is of exponential type, and what does it mean? Is that means that there exists some, now I should definitely use actually the variable, my variable will be denoted by z. Okay, so defined over this ring, and now I should say that actually, so the exponential type condition means that nabla is essentially a direct sum of isomorphic, and again this is over just C of Z formal variables. It's some direct sum of, and here I take constants in C, and then I want connection of the form d plus C over Z squared dz.
Excuse me, may I ask somebody? I'm on Zoom, Maxim Kontsevich. I cannot see anything. Maybe one can rotate the camera because I cannot see.
Yes.
Okay. Yeah.
This way.
Okay. Yeah.
Yeah. Okay.
Okay. This way. Okay. Yeah.
Okay.
So maybe you move the camera
No, not this one.
I think just this camera is shown on the Zoom.
There's no blackboard.
No black.
Okay.
Just
what?
this. Just this.
It's just this one, yeah.
So yeah.
That's what you see.
Now.
Right now you see the full board. Thank you. Right now I can see everything.
Okay. You can see. Okay, very good. Thanks. So okay.
Go on.
Yes, and so we have here there is a tensor sign and some nabla C reg. So what does this formula mean? So here I continue. So that this means that actually, so we have some points lowercase c. They are they form essentially the spectrum of the operator Euler product, and we can decompose actually in terms of the eigenvalues of the spectrum, and what is rest is something of regular singularities. Okay, and now this is what is meant by exponential step. So no root is needed. Yes.
So the quantum product is like a formal series in Z, right?
Right. And other variables actually.
What?
And other variables.
Okay, you're just a big problem. But then, so C are elements of the complex numbers still,
C
right?
are
They're not
complex
elements of like the Nabokov field or something.
No. They are really just honest complex numbers.
Okay. And in general, they'd be rational numbers because all the Gromov invariants are rational.
Right. I guess. Yeah.
Okay. They're really just rational numbers. Cool.
Maybe, yeah. Anyway, and so now we can talk about, well, then there is some reduction possible, because, one can study such objects, but since they decompose, one can just as well study the direct summands. And then, so reduction essentially, we can use the study to essentially C equals 0, because first of all we decompose into direct summands, we treat them separately, and from each direct summand it's possible to subtract C times Z over square by multiplying tensoring by some abelian element. So we can actually reduce to C equals 0, and in addition, in the general case, it's also, so from now on we'll just take C equals 0, and also we may assume just as well that, the leading order term, which is the term of order -2, is just maximally important. So it's maximally important. Leading order term, regularly important. In this expansion is regularly important. Yeah, very good. So the aim of the talk is actually to study such conditions. Okay, and again, they are related to atoms in the following way: is that actually atoms are supposed to be connected components of the spectrum, and then so we take the spectral cover associated to this nabla, and it has a bunch of connected components, has curves, and so it's clear that to any such C, I mean, if we have two different C's, then those curves cannot form the same connected components. So it's clearly related to opaques, to atoms. And now, okay.
But just to get the cardinality right, is some C's or is everything C?
Well, okay, yeah, very good. So the spectrum is by definition a spectrum of nabla is equal to the set of C's where this nabla C reg has dimension bigger than 0.
That right.
So I allow zero rank connections to.
Yeah.
So of course this is a finite. Yeah, but this is just a compact way to formulate this. And okay, so now I would like to consider a few words about, or say a few words about meromorphic connections and related objects. So meromorphic connections, because we have to deal with such objects, connections, and also lattices and regular singularity. And before I forget to say, an irregular singularity is a singularity that is not regular, which is kind of a triviality, but yeah. Okay, so now I will consider V to be C Z to some power direct on R, for some R figure, and at least 2. Yeah. And of course, and then we will consider something like, I will denote by omega the free module generated by CZ, by this generated over CZ by this symbol, formal symbol PZ. Okay, and then we have the notion of a connection that is associated to this. I mean, it's just a formal or a formal connection that is associated to this, namely. Okay, so definition here. The formal meromorphic connection What is it? It's a map. Is a map that I denote by nabla, which maps V, but cancelled over C to the power C double bracket Z. Every tensorialization takes is defined over C of Z, and then now to V tensor C of Z, and then I also tensor by this omega, and then I assume that the Leibniz rule is satisfied. I won't write Leibniz rule. Okay, and then so this is the notion of the meromorphic connection. Now. So I would like to introduce the notion of a lattice. Lattice in this module is the following. Of this V tensor C of double Z is just is a C double bracket Z submodule that is a basis over this ring. So such that when we tensor it by C of double Z, then we actually get back V tensor C of double bracket Z. So just an example is just V itself, but there are many other examples, many other modules in C double bracket Z submodules that generate the same module over C double parenthesis Z. Okay, and then what do we call a regular singular connection? It's just, okay, regular singular connection is following. Before continuing, okay. Before continuing, if we have a lattice, then there exists some sort of gauge transformation that connects V and V prime. Okay, so a remark, a fact is that so V and V prime are connected by some gauge transformation, which is just GL R C double Z. So this is maybe I should, yeah. I think I don't need to explain this. It's not unique, of course, but there exists some G. Now, yeah, and now, given such an element, it's possible. Well, this group acts on such connections, space of such connections, in a known way. So, definition, the gauge action. Formal gauge action of this GL R C Z on the affine space of connections on connections is by the well-known formula G dot nabla is equal to now I guess G circle nabla circle G. Now let me put G inverse here plus G inverse VG. Okay, where this is the well-known action, and then okay. Now assume that I'm given not only V, but I'm also given nabla. Then I want to define the notion of regular singular connection, which is the following. It's one for which there exists some gauge transformation, which brings it to nabla prime, which has only first order poles. This is the definition. So nabla. So what, maybe is this still the definition? Yes. So the connection nabla on V has regular singularities. If there exists some V prime and such that for this particular G that brings V to V prime, then we have that nabla prime equals G dot nabla has at most simple poles. at zero. So I'm only interested in behavior at zero. But now the crucial point here is that there do exist connections that have higher order poles, which are still regular singular. So it's after passing to another lattice that we must have first order pole, but not immediately over V. So over V, they can have several higher order poles. Okay, now this notion of irregular, regular, and of course irregular is the opposite. And what is Poincaré-Katz rank? I've already told it. Poincaré-Katz rank is essentially the if something has at most positive order 2, then Poincaré-Katz rank is at most equal to 1. Okay, so this is the kind of connections that we are interested in. Okay, very good. And now, any question so far? Okay. If not, then let me pass through the stack of such non-semi-simple connections. This is number 3. So I am in trouble in the sense that Ludmil pointed out several times that atoms do not form a category, but I will now introduce a category which is a wannabe version of a category of atoms, maybe. The point is that if one thinks about just connections and maybe just doesn't consider one just doesn't consider rational transformations, then one can really work with a functor, which is the following. Okay, so now we need to fix a bunch of data. So first fix are at least 2, and we actually fix some number, mu1, etc., mu r. These are complex numbers, and I will actually assume that they are non-resonant data. So what does this mean? Non-resonance. Non-resonant. It means that mu I is not the same as mu j mod z. Actually, a little bit less is a little bit weaker assumption would be enough, but for the sake of simplicity, this is a natural assumption. And then, what else do I need to fix? Well, I need to fix some positive number, and then I will set delta to be a disk of the disk of radius 1 plus epsilon in C, and O will be a set of holomorphic functions from this data, or sheaf of holomorphic functions. Sheaf of holomorphic functions over this disk of radius bigger than 1. And lastly, well, just some notations. Capital B is the standard Borel. I take it to be upper triangular. semi-integral subgroup, and it's very standard notation that I take lowercase b to be its Lie algebra, and n it's the potent radical. Okay, there it is. So B is the Lie algebra of B, and N is its nilpotent radical. So all of this. Okay, and now I will introduce. A groupoid. Okay. So, for lack of better notation, maybe non-semi-simple quantum connections, and it has this new vector here as argument. So it depends on this mu vector. It will be now a groupoid, which is who's okay. So let me. Yeah, I may want to put it on this board. So object it will be objects will be well nabla. It could consist of nabla and some frame. Yes. So where nabla is well, it's a meromorphic connection. I wanted to have first of all regular singularity. So nabla is a formal meromorphic connection. In V with poles of order. So okay, I didn't tell you what. Well, what do I mean by pole of order? So the connection matrix has pole of order at most 2. So whose connection matrix matrix has a pole of order at most 2, and I want it to be regular singular. So number is regular singular. So we have a regular singularity at the origin at z equals 0. But moreover, so it has a pole of order at most 2. So let me now really start to write formulas. So nabla should look like b plus k minus 2 z to the power minus 2 plus k minus 1 z to the power minus 1 and etc. times dz, and I want k minus 2 to lie in this nilpotent radical with k minus 2 belongs to n, k minus 1 should belong to b, and I also want that actually the monodromy k minus 1 is in B, and in addition k minus 1 should have mu1, mu_r in this order in the diagonal entries. This is how this depends on this vector mu. Okay, I want this, and in addition I want, so this has regular singularities. So now, even though this is just a formal meromorphic connection, the fact that it has regular singularities, then there's a theorem of Malagrange that applies, and it's possible to take a connection which is no longer formal but really defined over positive radius, and I want the monodromy of this regular singular connection to be to respect the standard flag. So it should look like this too. And now I should say something about this V1 VR. So this V1 vector at 1, etc. VR vector at 1 this is just some trivialization. So a frame of vector bundle at the point z equals 1. So now this is well defined because my whole thing actually converges over a disk of slightly larger radius than 1. So it's possible to take this. So this is a frame, and it should be invariant under the monodromy, preserved by the monodromy of lambda. Is preserved by the monodromy, and from now on I will denote the monodromy by T of lambda.
So when we present it like that, there is no need that there exists a category for which this is non-commutative course structure. These are not motivic in any way.
No, absolutely. So that's why I said that this is a connection theorist's version of atoms. It's pure. So let us forget about birational geometry. This is the kind of object that we get. Yes.
Sorry, this is naive, but if you have a frame that is preserved by an operator, then the operator is the identity, right?
Sorry. That is thanks. So the flag defined by this operator.
The flag bifunctional in minus was destroyed or something.
Yeah. So such that the flag. Thanks. Absolutely. So the flag whose flag is defined. Is preserved by the monodromy of lambda. Absolutely. Okay, so this is the angle of parentheses, and well, as you can see, there are many conditions. So right, but most importantly, this should have regular singularities, because I think of this nabla should take the place of nabla C, reg in a certain sense. So this is just the regular piece that appears in this decomposition. Okay. Now, what do I want to do with this? First of all, I must write. I said that this is a group weight, so I must write the morphisms. So the morphisms, luckily, they are much easier. They are gauge transformations by in C. So G is now in G, L, but only positive powers appear. And okay, so the first two, we must put some condition on the first two terms. So we have to write something like, we have to expand G in terms of powers of Z, and then the condition is that G lowercase 0 belongs to the Borel subalgebra subgroup, and G sub 1 belongs to the Borel subalgebra. So the jet to order 2 is upper triangular, essentially. Those are the morphisms, and of course they act on such data by the connection, on the connection I've shown how it acts, and actually now there's actually a convergence issue, so I must actually put this should be actually convergent over this disk. So how? Yeah, I think this is correct. So it's convergent. So it acts on. We evaluate G at 1, and then it will act on the frame. And it's clear that it will leave all these data invariant. Okay, so now comes, so this was a definition. Now for a statement, which is the following. Okay, so how shall I? So, and actually, my the main outcome of the theorem will be a corollary, which will say something about the coarse moduli space of this group weight. And before that, a little bit more technical statement comes first. And then there will be a simpler statement, which will be a corollary, which will come second. Okay. Now. So, okay, what do I need to rewrite? So, yeah, so essentially, what I need to write is that the following holds. So, if nabla is such a connection, so nabla meromorphic connection with regular similarity at 0, and what do I need? And then I can expand it into some power series of the form, or actually Laurent series of the form from n going to from -2 to infinity, so only at most second order for k and z to the power n dz. I have such an expression. Then the claim is that nabla actually extends to the whole CP1. This is extension property, and actually the way, the following way. So So over the trivial bundle, yeah, this is R times, of course. Okay, and then so with a second order pole and say so such that well, up to some gauge transformation of up to a gauge transformation GL are maybe not a constant, but over C of maybe rational is sufficient. We have nabla, so actually G nabla will look like as follows. It will be D plus just two terms, D minus 2, Z minus 2 plus D minus 1, Z minus 1, dz. Where D minus 2 is nilpotent and with D minus 2 in N and D minus 1 in B, and we even have some control over the eigenvalues in the diagonal, but not complete control. Here is now what essentially why we require non-resonance condition is that the following, so that and the with the diagonal eigenvalues, diagonal entries of D minus 1, now only mod Z are precisely the ones that we want, mod Z. So a different integer may be added actually to each one of these numbers. Yeah. And in addition, well, moreover, I mean, D minus 2 is conjugate to K minus 2. So K minus 2 was the degree 2 part of the original number. But this is kind of a triviality that it's conjugate, but yeah, it will play important role because the regularity is preserved this way. Okay, and moreover, this extension is unique up to some trivial up to what? Up to C star to the power R. So, well, we may rescale each basis vector of this new basis by some element of C star. Now, I promise to be okay. Maybe let me say a few words about this. How one can actually prove this statement. Essentially, the idea maybe goes back to the mean. So it's very similar to these idea of proof. Is due to Levin's book on differential equations with irregular singularities, and then it is possible to pick an extension to 0 with only first order poles. That's the idea of Levin, that this is doable. Because we have actually regular singularity, so there's no Stokes phenomenon arising, and in this context, actually, you just take any logarithm of the monodromy transformation, and then using that logarithm, it's possible actually to extend. But then one needs to modify this extension because because this condition may not hold, and then you modify this in a certain way. So let me, I think maybe.
We need to find G, or we need to find G.
That's right. Yes, and there is some way. So okay, well, actually, maybe let me call this lattice V1 prime VR prime. The lattice given by this procedure. And now I realize I'm wrong. This is right. Given by given by this procedure, and then modify it in some way to some V1 Vn. And how do we modify? First step is just take how we modify? Well, essentially, V1 will be Z to some power n1 times V1 prime for the unique n value of n1, where n1 is the unique integer is such that well, obviously, I want Z to the power n1 v1 prime to belong to my original lattice. But if I multiply it by n1, I think -1, then this is not an element of the lattice. But so this is obvious idea, and then we do this recursively like this. So for I bigger than 1, we do something similar. And well, for I bigger than 1, but we do something very similar. So essentially, we just take Vi, recursively. Let me just put it this way. We essentially take some linear combination, something like this, V I plus VI prime plus some other term. This is the minimal such value. But here I may actually allow singular coefficients. So this is, I mean, this is, it's not difficult enough to write out the details, but let me write the upshot. The upshot is that corollary is that this has this so this MS non-semi-simple connection mu has smooth, of course, moduli space, and actually it's an affine space. It's just n directs on n, so it's affine space of some dimension C r minus 1. Okay, and okay, I mean there's some details that are hidden at this point because it's not clear why I needed why flag is needed, etc. But flag is essentially there to rigidify the problem so that there are no non-trivial isomorphisms, and then if we remove isomorphisms, then we are just left with essentially the entries of d minus 2 and d minus 1. Those will really give coordinates for the close moduli space. Okay, so I guess this is all I have to say about atoms, and thank you for your attention.
So can I ask one question?
Yes.
So I mean, your talk can be translated into the language of, for example, p-adic analysis, in the sense that
a lot of these things, yeah, lattices definitely make sense for p-adics
and p-adic differential equations and so on.
Absolutely, yes, absolutely. I don't know, I'm not an expert, of course, of that aspect, and maybe there are some surprises, but a lot of this can be actually, yeah, this is just a valued field, and yeah, field evaluation.
The gauge group will turn out to be GL2 of a two-dimensional local field kind of thing.
Right, absolutely.
Which is a very interesting
GLR of QP
double bracket T.
Double bracket T, yeah, I think double bracket, yeah.
So I mean that's a very interesting thing now theoretically also.
Probably this aspect needs to be explored. But as soon as one has valuations and the connection is some operator that behaves well with respect to valuations, it probably has a counterpart, but I cannot state. Maybe everything goes. I don't know. One needs to check.
Questions?
So the objects here are connections, but the objects in the atoms were Hodgson homology groups of some exceptional collection. So what's the translation?
So I guess the way, I don't know, the way I think about them, or actually, well, this is definitely Ludmil is much more expert than me in the room, and but for me, yes, for me they are connections because I know about connections, but there are probably many other different ways to define them. And yes, I'm eager to learn other aspects too, but I cannot really say anything different than this.
In simple terms, and that will be repeated many times, atoms, you take the P-side force structure and impose on it the A-side force structure. Therefore, it has a double nature, dual nature. As a non-commutative force structure, as it was said, and a force structure in a classical way, part of the dynamic homology of your variety, which is compatible with the action of the manifold Tate group. Tony will say this in much more detail tomorrow in the first talk. Other questions? If not, let's think, do a break and then we listen to Prana.
geometry.
Thanks a lot, Ludmil. Thanks for the invitation to this conference. This year has special significance for me because both my PhD advisor, Tony, who's going to give the first talk tomorrow, and my postdoc, Ludmil, are from Bulgaria. So and this is my first time here. So this visit has special significance for me, and I'm really excited to be here. Also, I'm going to talk about a topic that, as many of you have seen, this program was funded by a grant or a project on categorical Kaehler geometry, and so I'm going to tell you a bit of a story about categorical Kaehler geometry. And the two words here is very important because we don't yet have a complete theory of, or good solid theory of categorical Kaehler geometry, but I want to tell you some story about the progress we've made and some of the ideas involved. Okay? So there are two aspects to this categorical Kaehler geometry. It's a categorical theory, there's some categorical geometry, and then there's the Kaehler aspect. So I want to first just review categorical geometry, which a lot of the talks today have actually been about that. So here's the definition. Kontsevich is that, so let's pick some, throughout I'm going to check some field K. Then non-commutative space over K is a K-linear stable infinity category. So maybe you're used to some other terminology. You might want to think of this as a K-linear DG category or a K-linear A infinity category. They're just different names for the same thing. So what's the idea behind this definition? In retrospect, one way one can motivate this definition is that by the cobordism hypothesis, if you have C some K-linear category, it gives rise to an extended 2D topological field theory. Which you can think of as an open string, topological open string background. What does that mean? So I'll just say this in words, but this is just motivation anyway. So the idea is that you might be studying strings propagating in some space, some Kaehler manifold times R31, and typically in string theory what you're interested in is in the correlation functions, the way the scattering amplitudes for strings, and those can be encoded in a two-dimensional conformal field theory. So in string theory you really don't start with a target space-time, but you just start with a two-dimensional conformal field theory, which is the world sheet theory, and you try to extract all the invariants you want of your would-be target space from that starting point, from your string background. Right? So Eguchi and Zhang taught us that you can take one of these 2D conformal field theories. If they have n equals 2, 2 supersymmetry, you can form these two topological twists, the A and B models. And those A and B models are now topological string theories, and they're encoded in an extended two-dimensional topological field theory. And the cobordism hypothesis says that giving one of these things is the same thing as giving a K-linear infinity category. So it's really some way of encoding the open string correlation functions in topological string theory. And also what this cobordism hypothesis says is that given this open string theory, you can extract from it a closed string theory. So to the circle, for example, you associate the Hochschild homology, and to any cobordism, two-dimensional cobordism whose boundaries are unions of circles, you get operations on the Hochschild homology, which encode things like we've been hearing about today. The closed string invariants are encoded in this Frobenius manifold structure, which is exactly what you get on this Hochschild homology space when you take into account circle action and do non-commutative Hodge theory and so on. So really this is related very much to the other talks we've heard today. Okay, so that's what one of these non-commutative spaces is. So let me just quickly say a couple of words about what K-linear stable infinity category is. So an infinity category is some category where there's a notion of mapping space between two objects. So given any two objects, there's a space of objects, a simplicial set if you like, or topological space. And you say that it is stable if there exists a zero object, which means that there's some object 0 with map E0 is contractible, is contractible and is equivalent to map 0E for all E. Then you assume that finite colimits and limits exist. And the key axiom is that, so well, since you have finite limits and colimits, you have push-out squares and pull-back squares, and the key axiom is that EFGH is pullback if and only if it is a push-out. And in particular, you have these special push-out pullback squares, which are the suspension and looping. This is an example. And so from this you get a notion of exact triangles. So this is where triangulated categories come from. And the way you can see that you get a map from G E shifted by 1 is that if this is a pullback push-out square, then you can form this bigger square. And because the outer square is a push-out square, this is E shifted by 1, and now you have this push-out square and this push-out, so these both are pullback push-out squares, and so you get this usual picture of triangulated categories. You get these maps E, F, G, E shifted by 1. Okay, so we want to take one of these categories and think of them as a space and study it. So there's two moduli spaces you can construct. Starting from a category, you can study the deformations of an object in the category, or you can study the deformations of the category itself. So given C, you get some functor MC from connected BG algebras, commutative BG algebras, to spaces. You can think of this as S-set, simplicial sets, if you like, which is characterized by the mapping space from any x into MC is the same as functors from C into perf x. So this MC you might think of as the moduli of objects in X. In C. It's a moduli functor which parameterizes objects in C. And you can ask if it's representable in some sense, if it's a nice space. And there's a theorem that if C is nice, technically if C is a finite type, so in particular if C is smooth and proper, so this theorem, so when Svejoul theorem of Cohen and Bakia, and I give a different proof in the smooth and proper case, then this MC is representable by locally geometric derived stack. So it doesn't matter if you don't know what these words mean, it just means that it's representable by space in some nice sense, Roughly speaking, it means that there's a simplicial object in derived affine schemes whose realization is this stack, and such that all the face maps are smooth. Anyway, so my point here is that there's a nice space parameterizing objects in the category, but it's nice in some very, well, depends what you think is nice. There's some huge derived stack parameterizing these objects, and you would like to understand this space in some more concrete way, right? So, question is, can you understand and see in some more concrete way? So in other words, can you understand some substacks, for example, which are actual projective or quasi-projective varieties? That's the kind of question you might ask. And the other question you might ask is whether you can define some geometric structures on these moduli spaces. And again, this comes from thinking about, if you like thinking physically, you should think of these objects in the category as boundary theories, two-dimensional boundary topological theories. So this is like a moduli space of two-dimensional boundary theories. And one of the question I'm going to ask today is related to the following thing physically, which is you can ask whether these topological boundary theories come from topologically twisting some boundary conformal field theory. And the answer to which ones come from a boundary conformal field theory is given by a notion of stability, which is called pi stability. And VIHREN gave us the axiomatic way to think about these things, which I'll come to in a second. Any questions at this point? Okay, so let me just quickly mention that you can also study deforming C itself. So let me just state it here now. I won't go into this in much depth. This is just to say that just like you can study the boundary theories, the moduli space of boundary theories, you can also study the moduli of the closed string background, which is the deformations of C itself, and that's given by the following. So the natural map, so there's a natural map from deformations of C over the formal power series ring to space of solutions to the Moravec equation, equation dx plus half xx equal to 0 in one-shifted Hochschild cochains, which is an equivalence of spaces. So for a long time, people seem to think that, I mean, you read all these things which would say that deformations of categories are given by solutions to the Moravec equation in Hochschild cohomology. That's not quite right, because the general solution to Moravec equation in Hochschild cohomology gives you a curved infinity category. And curved infinity categories are objects that I don't understand very well because there isn't a good notion of equivalence between them. You can't define cohomology and equivalence. So what this theorem really says is that every curved deformation, if C is tamely compactly generated, then this is true. Some very mild technical hypothesis says that every curved deformation of your category over the formal power series ring can be uncurved. And you can study this formal moduli space completely using just the Hochschild cohomology as a DGB algebra, or as an E2 algebra, actually. And again, this is very interesting for what we saw, the talks we saw today, because the Hochschild cohomology space is the thing that carries the structure canonically of the Frobenius. I mean, this is the tangent space to the moduli space of categories, and that should carry a Frobenius structure. Okay, but I'm not going to talk about this today. I want to focus on the first moduli space, the moduli of objects in a category. And incidentally, we used, to prove this theorem, you had to use simultaneous deformations of the category and an object in it, a compact generator in the category. So in some sense, ideally one should study both these moduli spaces together, and that would be like deforming the closed string background and the open string background simultaneously. Okay. Now to study NC, I want to introduce the notion of non-commutative Caehler classes. Which are VIHREN stability conditions. So let me remind you what these are. So VIHREN stability condition on C is given by two pieces of data. An additive homomorphism for the central charge from K0 of C, the Gothindi group of the category, into C, which is really, we should think of this as additively as R2 with a chosen orientation coming from C. And we'll assume that this factors through some gamma, a finite rank lattice. Right, so this really means you can start drawing a picture of your category in the complex plane. So for every object, you have some Z of E, and the statement that this is additive is the statement that if you have a triangle, then Z of E plus Z of G a triangle in this abstract categorical sense translates into an actual triangle in the complex plane.
So it satisfies the system relations in the, or how should I think about this?
That every time you have such an exact sequence, exact triangle, the central charge of the middle guy is the sum of the central charges.
Yeah, but that's kind of like what K naught of C does, right?
Yeah, so I'm just writing out what it means to say that this is an additive map. I mean, a picture somehow, I think, conveys more than the text. That's the only reason for writing that. Okay, so that's one piece of data, and the second piece of data is what's called a slicing. So for each theta in R, we give ourselves some full subcategory inside C, such that some axioms hold. So what are the axioms? Well, these are compatible. The first thing is a compatibility between the central charge and this notion of semi-stable objects. So E is, so these are called semi-stable objects. Of phase theta. So we want that if E is semi-stable of phase theta, then E sits in the ray so in other words, sits in the ray of angle theta. The second axiom is that if I shift everything, the angle by pi, that corresponds to shifting the object by 1. So C theta semi-stable shifted by 1 is C theta plus pi semi-stable. So if E sits here, then Z of E shifted by 1 sits there. And there's a technical axiom called the support property, which I'll just draw a picture of. It says that there is some comb such that this is the kernel of Z, and there's some cone containing it such that all the semi-stable objects sit outside it. These are the where E is semi-stable, where C semi-stable is just the union over all theta of C theta semi-stable, of all the objects of C theta semi-stable. Okay, so some technical property. And finally, the main axiom is this Harden-Nusselman property. It says that for all E, there exists some sequence of morphisms in the category, which you can think of as a filtration. So since we're in this triangulated stable infinity world, there's no notion of sub-object, but there's just a notion of morphisms. And so filtration is just a sequence of morphisms such that the cofibers of the successive maps is semi-stable of phase theta, theta I, with theta 1 bigger than or equal to bigger than theta 2, and so on, decreasing phases. Again, the picture is probably worth more than all the words. So if you have some object with slope given with some central charge in the complex plane, it has this filtration such that the associated graded pieces have decreasing slopes, which means that there is a kind of polygon sitting above Z of E, which encodes the central charges of the associated gradient. Okay, so that's what a stability condition is. And the space of stability conditions has many nice properties. So Bridgeland proved that the map from stat C, the space of stability conditions, with some natural topology to form from this lattice gamma of C, which sends a pair Z C theta semi-stable to Z is a local homomorphism. And so this space stat C is a complex manifold. Complex manifold with many nice properties, and for all the various examples of non-commutative spaces, the space of stability conditions has some nice interpretation. So the spaces we want to keep in mind are the following. So we have examples of spaces. So we've already seen X omega symplectic. Then we have the Fourier category. And conjecturally, a stability condition on this, I'll come back to this in a few minutes, is given by a holomorphic volume form on X with respect to some almost complex structure. If X is a complex manifold, Oh, actually, before I do this, I want to include one generalization of this, 1 prime. If you have a morphism x to p, a symplectic fibration, maybe y to x, y to x, a symplectic fibration, then this gives rise to some sheaf of categories on X, whose fibers are the Fukaya categories of this fibration. And at the singular fibers, you have some extra structure which encodes the singularities. And this data is called a Perber-Schober. So for those of you who know what this is, I won't give a formal definition. You get a Perber-Schober on X, conjecturally, all this is conjecture. And so you get Fukaya of X with coefficients in Y. And if I have time, I'll come back to how categorical Caehler geometry applies to this setting. The main example you want to keep in mind is that the base is some Riemann surface, and this is some symplectic fibration over Riemann surface. And you have a sheaf of categories over it. And in that case, the objects of this category can be described quite explicitly. There are some graphs on the Riemann surface whose edges are labeled by objects in the sheaf of categories. And so this is related to spectral networks. And in fact, understanding Caehler structures on these categories was the starting point for our project. We were trying to understand, prove a conjecture that spectral networks represent Brisbane stable objects in certain categories, and that's where this whole project really started. Okay, so, of course, when you have the B-model version of this, so in this case, a Brisbane stability condition is supposed to come from the Caehler parameters, so knowing the symplectic form, this should give rise to a stability condition. And finally, we have this toy model, which is the derived categories of representations of Q, where Q is equivalent. So these are the examples you want to keep in mind, and we want to understand how to construct Brisbane stability conditions, and yeah. Okay, so what I want to do next is I just want to make one more definition so that I can state a theorem which will seem a little mysterious, and then I want to explain how this whole categorical Caehler geometry story brought us to this theorem. So let's make this definition. So let's say we have C, some center charge, and this notion of semi-stable objects. Then, well, first of all, I should say the theorem, the VIHREN, is that if you consider the set of objects C, well, let me make a definition here. If I is some interval, then we define Ci to be the set of objects E such that Z, the argument of Z of AI, belongs to I for all Hardy-Nusselt constituents. And the theorem is that C of 0 pi, or any interval of length pi, is an abelian category. And is the heart of a T structure on C. And also C, theta semi-stable, is abelian. Is not in abelian category. So now I can make the definition I want to make. C polystable theta, well, C stable theta is by definition the set of objects E in C theta semi-stable. So E is simple as an object of C theta semi-stable, i.e. does not have any sub-objects. Since it's abelian, I can talk about sub-objects. And C polystable objects of phase theta this is by definition the set of E in C theta semi-stable that is a direct sum of simples, so there's semi-simple objects is an object of E. And so we have this notion of polystable objects, and the goal is going to be to construct, so the goal of this categorical Caehler geometry project will be to construct some Caehler metrics on these moduli spaces of polystable objects, and to define some structure which does that, and also to give an interpretation of polystable objects in terms of some differential geometric data. So, yes, so let me, maybe before getting into that, let me state a theorem. So we'll consider the following special case for this theorem. Let us say that our we're given functors fi from C to the power of k, and we can define and some numbers zi in the complex plane. Then we can define z of E for E any object in C to be the sum Zi times the Euler characteristic of Fi of E. Then this is active, this defines the central charge. And given this data, we can define also a line bundle so I want to introduce this notion of categorical line bundle. What this does is it assigns to every object E in C some line LE, one-dimensional vector space over K, and if you have an exact triangle, and this gives rise to an isomorphism LF and automorphisms of E acts on LE. So this is the kind of data you get out of this. You can define a line bundle with L at some E is the tensor product over I of the determinant of Fi of E. Just make sure I get the right. Yes. So then,
so excuse me,
yeah,
it's line bundle over where?
So it's line bundle in this formal sense, but in a moment I'm going to use it to define a line bundle on the or at least on the moduli space of polystable objects. So so this gives rise to a line bundle in the usual sense. And then the theorem in progress only because we have to fix technical things like saying in what sense this C theta polystable is a projective variety, quasi-projective variety, and so on. But morally, this theorem is straightforward to prove, is that this class is positive on right, so this is a Caehler class. It's an actual Caehler class on some variety, if this was a variety, so that's where the technicalities lie. But just formally checking this positivity is a consequence of the axioms of bridge instability. One can sort of prove this formally, modulo those technical questions. So whenever bridge instability arises in this way, we have this kind of formal positive class on the moduli space. So what's an example of this? And this example is the one I want to study. Is if you have a quiver Q, and you can study its representations. So you have some quiver, which is a directed graph. And you can study its representations, which are given by some vector spaces, EV, and some morphisms, so EU, EV, and some morphisms between the vector spaces associated to every arrow. So the category of such things is an abelian category at Q, and I can take its derived category. Or equivalently, I can take complexes of vector spaces at each vertex and morphisms of complexes of vector spaces, and then invert quasi-isomorphisms to get a derived category of representations. Now, what are the functors? So one way to get these functors Fi is to take Fi to be Hom from script Fi. The set of i's will be a set of vertices of Q, and the functor f sub v will just be Hom from script f sub v to blank, where script f sub v is one-dimensional vector space at vertex v, 0 otherwise. And so it just picks out, it just sends a representation to the component sitting over the vertex u or v. Right. And for each index v, we should give a complex number. So I give myself some complex numbers, zv. Some complex numbers zv in the upper half plane, and the central charge is just defined to be the sum over vertices of Q of zv times the Euler characteristic, well, zv times dimension of EV, and more generally z of some complex of representations would be the sum v in vertices of Q zv times the Euler characteristic. So this is an example of the situation, and in this situation you can actually construct a moduli space and give a description of the polystable objects in terms of solutions to an equation, which is King's equation, which is what I want to discuss next.
So in this theorem you don't need any assumption on K?
So, well, the key is here, so this is so the key is here that, well, if I interpret what it means to have a moduli space of objects in a suitably general sense, then this is true. But if you want it in the literal sense of like C, theta, this is an actual quasi-projective variety, then you probably need some hypotheses on C to say what that is.
So I mean, you assume this moduli space is algebraic variety?
Yeah, let's assume the moduli space is algebraic variety.
Then which condition on
this
C
is formal.
can guarantee that? And which condition on C can guarantee this moduli space is algebraic?
I don't know, it's a question of, I don't know the answer because it's a question about some good moduli spaces existing. We have this global derived stack, and then you have to construct some coarse moduli spaces using GIT. So, or some generalized beyond GIT construction. Okay. So the question really is, can we refine the scalar class to a Caehler metric? That's the question. That's one question. And the second question is to give a description of C theta polystable along the lines of Johnson and McYow. So a differential geometric description of this moduli space. Okay, so let me say how this works in some special case, but let me state the theorem first. So you might wonder, well, being polystable is stronger than being semi-stable, and the Harder-Nussmann filtration says that every object can be decomposed into semi-stables. So you might wonder whether there's a final decomposition of any semi-stable into polystables. And let me just state a theorem that says that's true. So this theorem has appeared in some paper that's in JDG last year. The Harder-Nussmann filtration admits the canonical refinement to the filtration whose associated gradient to a filtration to a R infinity filtration labeled by R infinity with the lexicographic order, whose associated gradient pieces are polystable. And in the interest of time, I won't get into the precise definition of this, the precise characterization of this filtration, but this admits a purely algebraic characterization. So it's uniquely characterized by some properties. And you might wonder where this refinement comes from, because if you take a semi-stable object and you ask for its decompositions into polystables, you're basically asking for a Jordan-Holder filtration of an object in an abelian category. And we know there are many Jordan-Holder filtrations. There isn't a special one. There's the Sokal filtration, the post-Sokal filtration, and there's lots of filtrations in between. What this term says is that if you have this center charge, this additional data, it picks out one special filtration, one special Jordan-Holder filtration. Okay. So how did we come upon this special Jordan-Holder filtration? It's by studying some metric structures in the special case of representations of quivers, and also motivated by heuristics from the A model. So what are these metric structures? So we put a Hermitian metric. There is the boxes here. So I'll put a picture. So we have a quiver. Here now I have a vector space EV, but I'm going to put a Hermitian metric HV on it, which you can think of as some unit ball inside the space.
So this is over the complex numbers.
Sorry?
This is now the
thank you, that's a good point. So now K is equal to C. So we put a Hermitian metric on this guy. And if you have a Hermitian metric, then what you get is you can analyze these maps T alpha and look at how much they rescale the unit ball. Another way to say that is that you have I-joints, T star alpha, and the singular values of T alpha times T star alpha measure how much the unit ball here is rescaled in various directions when you map it into the other guy. Right? So if you put Hermitian metrics, you get this I-joint, and that buys you something new, which is you can define this operator P in endomorphisms of E, where E is the direct sum of all the EVs, where P is defined by the sum ZV projection onto V, V vertices, plus the sum over alpha and arrows and if you had differentials in these representations, in other words, if I had complexes of representations, then I could add a term so you have this operator P. Now, this operator P, you can do various things with it. So you can define the central charge of E is the trace of P. You can define the mass of E to be the trace of the absolute value of P. So P is normal. In particular, you can diagonalize it unitarily, but you can write it as P is equal to P times where P is some self-adjoint operator, Hermitian operator, and this is also Hermitian. This polar decomposition. You can define a flow on the space of metrics which is given by this formula. And you can define a potential a complex value potential which will play the role of the Caehler potential. By the formula SC So you can define all these structures. Now, I want to emphasize that, okay, this seems like some arbitrary set of formulas, but they really come from thinking about A-model heuristics. So let me explain that for a second. But even before I say that, I want to say another thing, which is that this flow should really be thought of as the renormalization RG flow, the renormalization group flow for boundary theories. So the space of metrized, this MEP should be thought of as some space of QFTs, and this flow should be thought of as the RG flow. And the fixed points of the flow are exactly the polystable objects which represent boundary conformity theories. Okay, in fact, you can define a refinement of the structure. You can define also a measure mu E on R supported on the spectrum of this argument of P. These are just eigenvalues of our P, and the support of this guy here is just, yeah, I mean, I think I just say it in words. You look at the component. So if you diagonalize this matrix, the matrix looks like some real number e to the I theta 1, R2 e to the I theta 2, and so on. And so this is just R1, R2, and so on. It's a measure supported on finitely many points. And you can define the amplitude it's an interval inside the real line. This is the smallest interval containing spec of RP. And the nice properties of this are that the mass decreases with the flow. So this is a form of the G theorem for boundary theories, which says that there is a quantity which decreases along the RG flow. In the case of closed conformal theories, non-boundary theories, it would be called the C theorem, the homologic of C function, which decreases along the RG flow. So here we're dealing with boundary theories. This is analogous to the G theorem. This mass is a quantity which decreases with the flow. The amplitude shrinks. And the fixed points of the flow up to rescaling of metrics are the set of EH such that argument of P is theta times identity. For some theta. So these are called harmonic metrics. Of phase theta. So the theorem of King, reformulated, which is a kind of Donaldson-Wilbeck theorem, says that a representation E is polystable of phase theta if and only if it admits a harmonic metric of phase theta. Now this seems like, if you're familiar with King's theorem, this might seem like an unfamiliar sort of reformulation of King's theorem. I show you, if you just write out what this means, it really is King's theorem just reformulated. So where did it come from? Why I like things this way? This really comes from thinking about the A model. So this representation EH corresponds to some Lagrangian the numbers ZV in the upper half plane correspond to the volume form, homomorphic volume form. The operator P, well, also corresponds to the same thing because P was just constructed out of this. we get a measure. So note that this measure actually determines the central charge and all other quantities, because you can write z of e as the integral over r e to the square root minus 1 theta mu. So the measure here is defined as follows. If you have a gradient Lagrangian, then you have this map r omega which goes from L to R, and you can just push forward. You can define the measure mu L, measure on R, by mu L is just a push forward of the absolute value of omega along this thing, along this map R here. So the absolute value of P corresponds to the density absolute value of omega, and you can define this measure on the real line. And of course, you can define this central charge, Z of L, which is the usual thing. So the idea is that you can think of this Fukaya category is defined over this non-Archimedean field, and you can think of this analogy as saying that there's something similar happening with this category defined over a non-Archimedean field. EH is a harmonic metrization of phase theta, would correspond to saying that L is a special Lagrangian of phase theta. So the equation here was argument of P is theta times identity, and the equation here is that argument of omega restricted to L is theta constant. Okay, so that's the analogy that motivated this whole story, and there's a version of this analogy for Fukaya categories with coefficients, where the analog of special Lagrangians are exactly generalized spectral networks, a la Kaehler XT, and that's where we really started some of these discussions. So to convince you maybe that this whole so far I just showed you a theorem that is already known, King's theorem, but let me say two things. One is that the filtration, maybe I'll say this in words since I'm running out of time, the filtration I showed you earlier on polystable objects really comes from studying this flow on the space of metrizations. The asymptotic behavior of the flow as t goes to infinity determines this refined filtration, which is characterized purely algebraically, but it also has an interpretation in terms of the asymptotics of metrics as t goes to infinity under this flow, the flow which I erased, H inverse H dot P. So that's where, by studying this whole phenomenon, and this corresponds to the flow on the Lagrangian, which is an analog of the mean curvature flow. So to understand this, you have to see that deforming a Lagrangian in its Hamiltonian isotopy class, a tangent vector to the space of deformations of L is given by a C infinity function on L, because nearby Lagrangians are given by graphs of C infinity functions in a tubular neighborhood. And so the C infinity function is just arg of omega restricted to L. So by studying this flow, in the case of quivers, we get this refined filtration, which I described earlier. In fact, the theorem is the following for dp left q. The log of the norm of h of t grows like lambda 1 log t plus lambda 2 log t plus so on, plus O of 1 on the piece of the filtration labeled by That's the theorem. And finally, let me just say that there is a purely non-Archimedean analog. So you might wonder if we could prove a non-Archimedean analog of King's theorem, which applies to the Foucault category. And if you could, you would have proved this thing that's often called the Thomas-Yau conjecture, that there is a stability condition on the Foucault category whose stable objects are precisely special Lagrangians of phase theta. So that's a very hard theorem, and we've definitely not proven anything close to that, except in very, very special cases. But there is a theorem that you can prove. So I'll just take this theorem and stop there. So let's see, this is also in progress. So let the special be an adjunction. So this is the right adjunct. And so this gives rise to a comonad. F times G on this category CSP. And you just define C gen to be C met mod G C special. And suppose we are given a stability condition on C special, then I'm going to define a stability condition on this C generic. This is the category we're interested in. So you say that an object E in C gen admits a harmonic metrization if there exists a lift E tilde in C met such that E tilde restricted to, so f of E tilde is polystable of phase theta. Sorry, semi-stable of phase theta. In C special. And the theorem is that there exists a stability condition on C special, on C generic, such that C generic theta polystable objects are exactly those that admit is the same as C harmonic of phase theta. C harmonic are the objects that admit harmonic metrizations. So this is a kind of Donaldson-Ulrich theorem, and as a special case, you can consider the following situation. You start with a category defined, this is sort of a pictorial depiction. You have some category C special, and this is some non-Archimedean field. Think of like something like C power series ring in T, and C metrization is a model, is a category defined over the formal power series ring, and C generic is the general fiber over C Laurent series. And in this situation, you can apply this mechanism to prove this type of theorem. And the way this is proved is again using the flow, an analog of the flow that I described for metrizations of curves. So I'll stop there. Thank you.
One question.
So the quiver you used are arbitrarily chosen quiver?
Yeah, just take any quiver.
So if we change the quiver, the theory changes a bit.
If you change the quiver, sorry?
if we change the quiver, replace the quiver with another one, and
Yeah.
do the same argument, there will be some differences in the theory, right?
You will have a different state, a non-commutative space.
Yeah.
But the theory will work exactly the same. So
I
it's-
see.
yeah.
Yeah.
The notion of thing polystable, etc., will be different.
Yeah.
Yeah.
One more thing about quivers. Have you thought about volume of if they are constructed using quivers if you choose that one in particular one to happen?
That's interesting. I haven't thought about that connection. I haven't thought about how you can apply this to.
I see.
All right, so let's continue tomorrow at 10 o'clock with Don and Pantev talk. Just come down.
Terapia, Enrique,